Hello there, and welcome to Science for Sleep, where curiosity finds a soft chair, science takes its time, and the world around us becomes a little quieter for a while. Tonight I'd like to invite you into a question that is both simple and utterly strange. What if time itself, that unseen companion we live by, has an edge, just like space does? Not an end in the dramatic, apocalyptic sense, but an edge in the same way the Earth once seemed to have an edge to those first sailors who gazed at the horizon and wondered if they might tumble into the unknown. Before we go any further, I'd like to pause and ask you something. Where are you listening from tonight? Is it late where you are, or early? Do you have a clock glowing faintly nearby, or maybe you've set this playing in the background as you close your eyes? It's funny, isn't it, how we always mark ourselves against time. We can't help it. Even as we ask a question about time possibly having an edge, we anchor ourselves by asking, what time is it right now? Maybe for you it's just after a long day. Maybe you've tucked yourself into bed, hoping for rest. Or maybe you're halfway across the world, beginning your morning and slipping into a few quiet minutes before the noise of the day begins. Wherever you are, whatever hour your clock reads, I'm glad you're here. And while you're settling in, let me gently remind you, if this little voyage into questions and wonder feels soothing, or if it simply gives you a soft landing after the day, I'd be grateful if you liked the video and subscribed. It helps this little corner of calm reach more people who might need it. But that's just a small note. Nothing to dwell on. We're here for something bigger, and yet, in a way, smaller. We're here to think about the edges of time. Now, when we talk about edges, our minds often go straight to space. We think of the way the Earth seems to stretch until it disappears over a horizon. We picture the edge of a forest where the trees give way to a field. We imagine the shoreline where land meets water. But time doesn't feel like that. Time feels endless. It slips past us second by second, and even though our lives have beginnings and endings, time itself seems to go on. It's a river that doesn't stop flowing, or so we believe. But what if that isn't quite true? What if time has its own boundaries, a beginning, an edge, a place where it either started or must eventually stop? That idea can sound unsettling at first, but let's not rush into discomfort. Instead, let's ease into it as though we're unwrapping a puzzle. If you've ever looked out at the night sky, you've already seen edges of a kind. Not edges in the sense of a wall, but horizons created by distance and light. You can only see as far as light has travelled since the beginning of the universe. Beyond that, not because there is nothing, but because the light hasn't reached us yet. That's one kind of edge. So what would an edge of time look like? Would it be a horizon where moments cannot cross? Would it be the very first tick of the universe's clock? Or perhaps the final tick, far into the future when everything grows still? But before we try to describe it, let's step back and think about the way we usually picture time. Every culture, every language has found ways to represent it. Some see it as a line we move along, with a past behind us and a future ahead. Others see it more like a circle, repeating and looping. Some even picture it as a landscape, where events are places you can visit, and memory is like turning your head from one side to another. These ways of imagining time all help us navigate our daily lives, but none of them really answers the question of whether time itself is infinite, or if it could possibly stop, the way a road eventually runs into a cliff. It's a question we don't often ask in daily life. Most of us are far more concerned with whether the bus will arrive on time, or how long we've been waiting for the kettle to boil. But in those quieter moments, when you let your mind drift, you might notice the strangeness of it. Everything else in the world seems to have boundaries. Our lives do. Our planet does. Even the universe, vast as it is, may not be infinite. So why would time be any different? Let's try a thought experiment together. Imagine you're walking across a field that stretches endlessly. It seems as though there is no boundary, just grass and sky forever. But then, one day you reach a fence. It doesn't matter how far it extends in either direction. The fact that there's a fence at all tells you that the field has an edge. What if time works the same way? What if, no matter how far you go, there's a point you simply cannot move beyond? Not because you've run out of energy, or because something blocks your path, but because time itself doesn't extend further. This is where we begin to realize the subtlety of the question. If time has an edge, how would we ever notice it? Unlike a field with a fence or an ocean with a shore, we can't walk to the end of time and put a hand on it. Our lives are far too brief compared to the cosmic scale. And yet, by looking outward, by studying the universe, we've already found clues that time may not stretch without limit. The universe itself has a beginning. 13.8 billion years ago, there was the Big Bang. That's as far back as time goes, at least as far as we can measure. So in one sense, we already live in a reality where time has an edge. It began. There was a moment before which, according to most of physics, time simply didn't exist. But here's where things become fascinating. If time had a beginning, does that necessarily mean it must also have an end? Some cosmologists think so. They suggest that just as the universe began with the Big Bang, it may one day end in a heat death, or a collapse, or some transformation beyond our comprehension. In that case, time would not be infinite. It would be like a book with a first page and a last. We happen to be somewhere in the middle, flipping slowly along. Of course, not everyone agrees. Some believe the universe could go on forever, expanding endlessly, with time never reaching a final edge. Others think the universe might cycle, repeating over and over, with time looping back on itself. In that case, the edge of time would be strange indeed, less like a fence and more like a doorway that leads you back into the same field again. Whichever way you look at it, the idea that time could have an edge is not as far-fetched as it first appears. It's an idea whispered to us by the universe itself, if only we stop long enough to listen. And speaking of listening, perhaps as you're lying there, eyes growing heavy, you might notice that this whole conversation about edges has a soothing quality. Because even though we're dealing with something vast and mysterious, the way we explore it together is slow, gentle, and unhurried. There's no need to reach a conclusion right away. Just as you can't see the end of the night sky in one glance, we don't need to solve the puzzle of time in one breath. We can drift along it moment by moment, letting the questions carry us forward. It's not every day that we stop to ask whether time itself might have a border. Borders are things we usually associate with maps, with fences, with rivers and coastlines, with points where one thing ends and another begins. Time, by contrast, feels more like air. We don't often think of it as having limits, because it seems to wrap around everything we do, everywhere we go, every thought we think. It's there when we wake up. It's there when we fall asleep. It's there when entire generations pass by. We can't see beyond it, and so we often assume it stretches on endlessly. But every now and then, a question comes along that invites us to reconsider the obvious. What if time is not limitless? What if it does have an edge, a boundary, a point you simply cannot cross? To even begin to picture this, it helps to think about how strange the word border becomes once you take it out of the usual context. Imagine standing on the shore of the ocean. You can see where the water ends and the land begins. You can draw that line in your mind or even on a map, and you can say, here is the border between sea and shore. That feels natural, because the two sides are different. You can walk on land, but you can't walk on water. You can swim in the sea, but you can't swim in soil. The border marks a difference. So if time were to have a border, what would be on the other side of it? That's the heart of the strangeness. A border in space marks a transition between two regions. But a border in time would mark something even stranger, because on the other side of time, there may not be anything at all. For centuries, people have wrestled with this question without quite calling it that. Ancient myths often describe a beginning of time, usually in the form of creation stories. Something happened, or someone spoke, or some divine action took place, and suddenly time began. Before that, there was no before. Philosophers later argued about whether time must have always existed or whether it could have had a start. Even today, cosmologists debate the same issue, though now with the language of physics instead of poetry. The Big Bang, they tell us, was not just the beginning of space but the beginning of time itself, and so in a way the universe already gives us a hint of what it means for time to have a border. The very beginning is one, the question is whether there could be others. But let's pause and consider something simple. When we look at space, we know it can have edges of a kind. For example, the observable universe has a limit, a horizon beyond which light has not yet had time to reach us. If you could stand at that horizon, you wouldn't find a wall. You'd simply find that beyond it you cannot see. The information hasn't arrived yet. It's not a fence you can touch. It's a limit to observation. Perhaps time's border is like that too. Maybe there isn't a wall you'd crash into, but instead, a region beyond which before or after doesn't have any meaning. Now, think about what it means to live in a world where time might have such boundaries. We're accustomed to thinking of our lives as moving forward, moment by moment into the future. We don't expect to suddenly run out of moments. Yet when you think carefully, our personal lives do have borders in time. There is a before we were born. There will be an after we are gone. Those are temporal edges, though they are personal rather than universal. The difference is that when we speak about time itself having a border, we are talking about something larger than any one life. We're asking whether the whole structure of reality has edges, whether the timeline of the universe is like a rope with frayed ends, or whether it stretches without limit. This thought alone can bring a kind of dizzying feeling, as though you were standing on a cliff and looking down into something you can't quite measure. But that dizziness isn't a reason to turn away. It's an invitation to look more closely. If you've ever watched a clock and wondered why it keeps ticking, why there is always another second after this one, you've already brushed against the same question. A border in time would be the moment where no more ticks follow. The clock doesn't stop because it's broken. It stops because there is no more later for it to move into. And here we come to a curious point. Can we even imagine what that would feel like? Our minds are so shaped by time that we tend to picture it continuing no matter what. Even if you try to think of nothing after, your brain tends to imagine a long empty stretch, as though time was still passing but with nothing happening inside it. That is the trick. Our imagination smuggles time in even when we try to take it away. It's like trying to imagine the colour blue without actually picturing blue. The very tool you're using refuses to let go. Some philosophers have suggested that this difficulty points to something profound. Perhaps time doesn't exist independently at all. Perhaps it is simply a way of describing the order of events, a relationship between things. If that's true, then asking whether time has a border is a bit like asking whether numbers have a border. Do numbers stop at a certain point? You can count higher and higher, but the concept doesn't have an edge. But if time is more like space, something woven into the universe itself, then maybe it does have an edge. Because the universe has beginnings and may have endings. What makes this a strange question is that it puts us right at the intersection of science and experience. On the scientific side, we can look to theories of cosmology, relativity, quantum physics, and thermodynamics, all of which say something about beginnings and endings. On the experiential side, we are creatures who live in time, who remember the past and anticipate the future. So for us, a border in time isn't just a theoretical line. It's a disruption of the very way we understand existence. It's as if someone asked a fish whether water has an edge. The fish might swim to the surface and discover air, but what would it make of that? Perhaps you felt something like this when you've stood at the edge of the sea and looked out. You know, rationally, that the earth curves and that there is no actual edge. But to your eyes, the horizon looks like one. You can't see past it. It looks like a border, even though it isn't. That's the subtlety here. Sometimes what feels like a border is just a limit of perception. So when we ask whether time has a border, we also have to ask whether it's a real edge or just an apparent one, a horizon beyond which we cannot look. Now, this brings us to a practical curiosity. If there were a border to time, how would we know? Our tools are clocks, calendars, telescopes, equations. All of them are shaped by time itself. Can a tool that depends on time ever tell us whether time has an end? It's like using a candle to try to see beyond darkness that no light can reach. Still, this hasn't stopped humans from trying. The history of science is filled with attempts to peer past the horizon, to imagine what lies beyond the point where knowledge seems to stop. That, in a way, is what makes this such a compelling question. It isn't just abstract. It's at the root of our attempt to understand reality at all. And so, as you listen, you might notice your thoughts beginning to soften and stretch, much like time itself seems to do. The words flow one after another, not hurrying, not racing, just unfolding, giving your mind space to settle into the mystery. The strangeness of the question doesn't demand a quick answer. It simply asks you to sit with it, to let it turn slowly in your thoughts, to feel the edges of your own imagination as you try to picture something beyond time. If time does have a border, what is it made of? Is it a beginning, like the Big Bang? Is it an ending, like a cosmic heat death? Is it a loop, where the edge connects back to the start? Or is it something we can't even put into words yet? When we start thinking about whether time might have a border, it helps to first look at something we can picture a little more clearly. Space. Unlike time, space feels tangible. We can point to it, walk across it, map it, measure it. We can stand on a mountaintop and look across the land, or look through a telescope and see galaxies glowing billions of light years away. And yet, even space has limits. Not hard walls like a room, but edges defined by how far we can see, how far we can travel, and what the universe itself allows us to know. The most obvious edge we all encounter is the horizon. You've probably felt its pull. Standing at the seashore, looking at the line where the water seems to meet the sky, you can't help but wonder what lies beyond. The horizon isn't a real wall, of course. It's just the curve of the earth hiding distant places from view. Sailors once believed it really was an edge, a place where the ocean might drop off into nothingness. For them, the horizon carried mystery and danger. Today, we know that beyond the horizon, there's just more world waiting to be discovered. But the idea of the horizon has never lost its power. It's the first kind of edge we learn to imagine, not a barrier, but a limit of perspective. Astronomers face a similar situation, only on a much larger scale. When they look into the night sky, they too face a horizon. Not the curve of the Earth this time, but the curve of time and light. We can only see as far as light has had time to travel since the beginning of the universe. That distance is about 46 billion light years in every direction, even though the universe itself is only 13.8 billion years old. The expansion of space means that the light we receive today comes from regions that are now far more distant than they were when the light began its journey. This sphere, beyond which we cannot see, is called the observable universe, and it functions like a cosmic horizon, an edge of knowledge, beyond which lies mystery. What's striking is that this edge is not physical. There is no wall of glass at 46 billion light years. The galaxies beyond that distance are not cut off in reality. They're still there, still moving, still shining. We just can't see them because their light hasn't had time to reach us. The observable universe is an edge created by time and space together, a partnership between how far light travels and how old the universe is. So when we talk about the edge of space, we're really talking about a horizon in perception. It's the same feeling as standing on the shore, only now the ocean is made of galaxies. This idea has shaped how we think about the universe. For much of human history, people assumed the cosmos was infinite. You could keep travelling forever, and there would always be more stars, more worlds, more sky. It was only when we began to understand the speed of light, the expansion of the universe, and the finite age of everything that the idea of an observable edge became clear. In a way, this edge of space mirrors the question we're asking about time. If space can have limits in what we can observe, Might time also have such limits? And if so, what would they look like? But before we circle back to time, let's explore space a little more. Because space doesn't just have one kind of edge, it has many, depending on how you look at it. There are horizons created by black holes, for example. Cross the event horizon of a black hole, and nothing, not even light, can return. To an outside observer, the event horizon is the ultimate border, a point of no return. But from the inside, if anyone could survive such a fall, it wouldn't feel like a wall. You would simply drift through, carried toward the singularity at the centre. Again, an edge is defined not by material barriers, but by the limits of information and perspective. Then there are cosmological horizons. As the universe expands, distant galaxies move away from us faster and faster. At some point they move away so quickly that their light can never catch up to us. That creates a kind of future horizon, a border beyond which no signals will ever arrive, no matter how long we wait. Even if the universe lasts forever, there will be regions we can never know about, because the expansion has swept them permanently beyond reach. Imagine living in a house with windows that grow smaller over time. More and more of the outside world becomes invisible until eventually only your own room is left in view. That's what the accelerating universe is doing to us. The edges of what we can see are creeping closer, not because the universe is shrinking, but because its expansion is outrunning light itself. So when scientists speak of the universe's edges, they're not talking about walls. They're talking about horizons, shifting, relative boundaries defined by light, speed, and time. And this brings us to an important point. An edge doesn't always mean something ends. Often it means we've reached the point where our knowledge, or our influence, or our senses can go no further. Beyond that, reality may continue, but it becomes inaccessible to us. And isn't that an interesting way to think about time as well? If time has a border, maybe it isn't a wall where things stop. Maybe it's more like a horizon, a place beyond which the concept of before or after doesn't apply, or beyond which our observations cannot reach. Just as we cannot see past the event horizon of a black hole, perhaps we cannot peer past the horizon of time's beginning. The border is not made of stone, it's made of the limits of possibility. To make this more relatable, think about standing in a fog. You can see only a short distance. Beyond that, the world may well continue, but it is hidden. The edge of your vision is not the edge of reality. It's the edge of what you can know from where you stand. In the same way, when we talk about cosmic horizons, we're describing the edges of our perception, not necessarily the edges of existence. The observable universe is like standing in a fog that happens to be 46 billion light-years thick. You can see everything within that bubble, but what lies beyond is concealed, perhaps forever. The same principle applies when we think about the very beginning of time. The Big Bang is sometimes described as a wall, a point beyond which we cannot look, but really it's a horizon of sorts. Physics as we know it breaks down there. Our equations stop making sense. That doesn't necessarily mean there was nothing before. It simply means we cannot see past that boundary with the tools we have. The border is real to us, but it may not be absolute in the universe itself. This distinction between real edges and apparent horizons matters because it shows us how flexible the word edge can be. Edges are not always cliffs. Sometimes they are veils, sometimes they are doors, sometimes they are simply the limits of vision. And once you understand that about space, you begin to see how the same might be true about time. And here's another curious thing. Every edge we've found in space has taught us something about ourselves. The horizon at sea taught us about the curve of the Earth. The horizon of the observable universe taught us about the finite age of the cosmos. The event horizon of black holes taught us about the limits of gravity and light. Perhaps the edge of time, if it exists, will teach us something equally profound. Not just about physics, but about what it means to exist within a reality that has boundaries. As you think about this, let your mind wander a little. Picture the night sky above you, stretching in every direction. Imagine it as a great dome, though you know it isn't really. Imagine the stars twinkling at the edge of sight. Imagine galaxies further still, their light faint and old, carrying messages from a time when Earth itself was young. Then picture the horizon beyond that, the place where the light has not yet arrived, and ask yourself, what lies there? You don't need to answer. The act of wondering is enough. It is the same act that has driven explorers, scientists, and dreamers across centuries. To ask what lies beyond the edge is, in a sense, to be human. And while the question itself may feel vast, the pace at which we explore it doesn't need to be. There's no rush. Horizons are patient. The universe is patient. We can take our time, moving gently from space to time, from what we can see to what we can only imagine. Because the edges of space are only the beginning. The real strangeness waits when we turn back to time itself and ask how far it goes, and whether, like space, it too has horizons that define what can and cannot be known. When we talk about edges in everyday life, we usually mean something clear and tangible. The edge of a table is where the wood stops and the air begins. The edge of a cliff is where the ground runs out beneath your feet. The edge of a page is where the words give way to blank space. It's easy to picture, because our senses deal with these kinds of edges all the time. They're visible, touchable, and often a little dramatic. But in science, the word edge doesn't always mean the same thing. Scientists use it in ways that are subtler, sometimes invisible, and often surprising. To understand what it could mean for time itself to have an edge, we first have to think about what edges mean in science more broadly. Take the idea of an edge in physics. If you ask a physicist about the edge of the universe, they won't describe it as a wall you could bump into. They'll talk about limits, limits of observation, limits of measurement, limits of what the equations can describe. In other words, edges are often places where our knowledge, or the rules we rely on, stop working. It's not that reality stops, but that our ability to describe it runs out. A border in this sense is less like a cliff and more like the end of a map. The land may continue, but the chart says, "Here be dragons," because we don't know what lies beyond. Another example comes from chemistry. Think of the edge of matter itself. For centuries, people wondered whether matter could be divided endlessly, smaller and smaller without limit. Eventually, scientists realized there is an edge of sorts. The atom. You can't divide matter forever. You reach a basic unit, a border beyond which the concept of ordinary matter no longer applies. And then, when physicists looked even closer, they found smaller particles inside the atom, and then deeper still, quarks and gluons. Each time, what looked like a final edge turned out to be another layer. But the idea remained the same. Edges in science often mark the point where one description stops being useful and another begins. You can see the same principle in astronomy. Before telescopes, the stars were thought to be fixed points on a celestial sphere. That was the edge of the sky. Then telescopes revealed moons, planets, galaxies. The edge shifted outward. The more powerful our instruments became, the further the edge moved. What we call an edge often turns out to be a temporary frontier, shaped as much by our tools as by the universe itself. This should remind us of something important. In science, edges aren't always final. They're often horizons that move as we learn more. The event horizon of a black hole, for example, is not a wall in space, but a mathematical boundary. It's the place where escape velocity exceeds the speed of light. Nothing can cross back once it goes in, not because there's a barrier to push against, but because the laws of physics forbid it. To an outside observer, that's the edge of visibility. To someone falling in, there's nothing unusual at the horizon at all. The edge exists only in relation to perspective. That idea of perspective is crucial. In relativity, what looks like an edge to one observer might not look like one to another. The twin who travels at near light speed will experience time differently from the twin who stays home. For the traveller, the edge between years and moments is blurred. What feels like a long journey for one is a brief trip for the other. So in science, edges can be relative. They depend on where you stand, how you move, and what tools you use to measure. It's also worth thinking about edges in terms of mathematics. In equations, edges often appear as infinities, places where the numbers blow up and the formulas stop working. In calculus, they're called singularities. In physics, singularities appear in some of our deepest theories. The centre of a black hole is one, the Big Bang is another. These singularities are not necessarily places in space or time you could visit. They are edges in the math, signalling that our current theories are incomplete. They mark the border between what we can calculate and what we cannot. So when scientists say the edge of the universe, or the edge of space-time, they're not picturing a brick wall in the cosmos. They're acknowledging the limits of our models. They're saying, here's where the equations stop making sense. Here's where our instruments can no longer see. Here's where the concepts we rely on no longer apply. The edge, in this sense, is as much about us as it is about the universe. It's the boundary of our understanding. Now let's apply that thinking to time. If time has an edge, it might not be a literal cliff where the seconds stop falling. It might instead be a singularity in the math, a place where our descriptions no longer hold. The beginning of time, the Big Bang, is one such edge. Our equations break down when we try to describe what happened at the very start. Physics as we know it can describe the universe a fraction of a second after the Big Bang, but not the precise instant itself. That moment is an edge, not because reality necessarily ends there, but because our knowledge does. This way of thinking helps us reframe the question. Instead of asking, does time itself stop? We might ask, do our descriptions of time stop working? That is often what scientists mean when they talk about an edge. The distinction matters, because one makes the universe seem finite in a dramatic way, while the other highlights the limits of human understanding. The universe may have no end, but our ability to describe it might. There's also another layer to this. In science, edges often generate new theories. When Newton's laws reached their edge, Einstein's relativity stepped in. When classical physics reached its edge with atoms, quantum mechanics emerged. Each edge is a signal that something deeper is waiting to be discovered. So if time itself has an edge, it may be less a stopping point and more a doorway, a clue that a new description of reality is needed. That's why cosmologists are so fascinated by the beginning of time or by the interiors of black holes. Those are the places where the edges are sharpest, and therefore where new discoveries are most likely to emerge. Think too about the way edges function in biology. The cell membrane is an edge. It separates the inside from the outside, but it is not a wall. It's a semi-permeable boundary that regulates flow. Without that edge, life couldn't exist. Edges are not always places where things end. They're often places where interactions happen, where inside meets outside, where new dynamics appear. In that sense, maybe the edge of time, if such a thing exists, is not a void but a place where something new begins. The beginning of time might not have been the end of nothingness, but the birth of everything. This should make us cautious about how we picture the word edge. Our daily lives train us to think of it as something final, a hard stop. But in science, edges are often thresholds. They are places of transition, where one regime gives way to another, where old descriptions stop working and new ones are needed. The edge of liquid water at 0 degrees Celsius is not an abyss. It is the transition to ice. The edge of air at high altitudes is not nothingness. It is the thinning of one medium into another. The edge of vision in your eye is not the end of the world. It's simply the limit of your receptors. So when we ask what an edge of time might mean, we should be open to many possibilities. It could mean a beginning, like the Big Bang. It could mean an end, like the heat death of the universe. It could mean a transition, where time as we know it gives way to something else we don't yet have the language to describe. It could even mean a horizon, a limit of observation, beyond which time continues in ways we cannot see. And perhaps most intriguingly, it could mean that time itself is not fundamental. Some physicists suspect that time may be emergent, not a basic ingredient of reality, but a phenomenon that arises from deeper rules. If that's true, then the edges of time might mark the point where those rules change. Time may not stretch forever, because it may not be a thing in itself. It may only exist within certain conditions, like temperature does. In that case, the edge of time would be wherever those conditions stop being true. All of this may sound abstract, but it has a simple grounding. When scientists talk about edges, they're talking about limits. Limits of perception, of description, of applicability. Edges mark where one picture stops working and another is required. They are less about endings and more about transitions, and in that sense, asking whether time has an edge is not about whether everything suddenly halts, but about whether our current understanding is brushing up against a limit. The comfort in this is that edges are not necessarily frightening. They're invitations. They tell us there is more to discover. They tell us that what seems complete is not the whole story. They tell us that reality has layers we have not yet peeled back. So when we imagine time having an edge, we can think of it not as a dead end, but as a new beginning, waiting quietly at the horizon of our understanding. Having thought about what edges mean in science, as limits, as thresholds, as places of transition, we can return to the cosmos itself. If time has such edges, where might they be? We've already touched on the beginning of time. But what about the far future? Could there be an edge waiting ahead just as there is one behind us? And when we think about edges in the universe, it is tempting to imagine something dramatic. Perhaps a cosmic wall, some vast invisible barrier that says, here is the end of everything. Our imaginations love to conjure cliffs, fences and borders that can be touched or crossed. But in reality, the universe's edges are more complicated. They are not walls of stone or sheets of glass. They are woven into the very structure of space and time. And if we are to ask whether the universe is expanding yet finite, we need to carefully untangle what that could possibly mean. The first thing to notice is that space itself is not static. For a long time, people assumed the cosmos was fixed and unchanging, a grand stage on which stars and planets moved but which itself remained still. That picture shifted in the 20th century, when astronomers discovered that galaxies were not only moving, but moving away from each other. The further away a galaxy is, the faster it appears to recede. This observation, made by Edwin Hubble and others, led to the conclusion that the universe itself is expanding. Space is stretching. Distances are increasing, not because galaxies are rushing through a static void, but because the fabric of the cosmos itself is growing. This expansion leads us to one of the most curious questions in all of science. If space is expanding, does it have an edge? Can it be finite in size, but still have no boundary? The answer, as strange as it may sound, is yes. Mathematically, it is possible for space to be finite and unbounded. To see how, consider the surface of a sphere. The Earth, for instance, has a finite area. You can measure its surface and get a definite number, yet it has no edges. You can walk in any direction, and you will never encounter a wall or a cliff that marks the end of the surface. You will simply loop back around. In the same way, cosmologists think the universe could be finite in extent, but without edges, curving back on itself in higher dimensions. But there's another possibility. The universe could be infinite. Space could stretch on without limit. No looping required. In this case, the observable universe, the region we can see, would still have an edge defined by the distance light has travelled since the Big Bang. But beyond that horizon, space might continue forever. Both pictures are consistent with what we observe, and both challenge our everyday intuitions about edges. One says that space is like the surface of a sphere, finite but edgeless. The other says it is infinite, with our observable patch being just a tiny part of the whole. Now, what about the expansion itself? If space is expanding, what is it expanding into? This question often comes up, and it makes sense to ask it. When you picture a balloon inflating, you imagine the surface expanding into the surrounding air. But the universe is not expanding into anything. It is not a balloon in a room. It is the room itself, and the expansion is the stretching of space between objects. From the inside, we don't need an outside. The distances increase, but there is no external void being filled. That's another way in which the universe defies our everyday notions of edges. Still, expansion does create horizons, and horizons are a kind of edge. For example, because the universe has a finite age, there is a maximum distance from which light could have reached us. That's the observable universe. Beyond it, there may be countless galaxies, but they are forever hidden from us because their light has not had time to arrive. This is an edge created by time and expansion together. And expansion doesn't just set a past horizon, it sets a future one as well. If the universe continues to accelerate in its expansion, there will come a time when distant galaxies recede so quickly that their light can never reach us. One by one, galaxies will slip beyond our cosmic horizon, until eventually only our local group of galaxies remains visible. To future astronomers, the universe will appear dark and empty, not because it truly is, but because the expansion has pushed everything else beyond reach. The edges of the observable universe will creep inward, not in space, but in what can be known. So when we ask whether the universe is expanding but finite, we have to be precise about what we mean. Finite in what sense? Finite in observable size? Yes, because we can only see so far. Finite in overall extent? Possibly if space loops back on itself. Infinite in extent? Also possible if space simply stretches forever. Each option carries its own version of edges, some real, some apparent, some hidden in mathematics. This brings us back to the earlier point that edges in science are often about limits of description. For the universe, the edges we talk about are not places you could travel to and put your hand against. They are horizons of light and time. They are boundaries set by the age of the cosmos and the speed of expansion. They are as real as anything we measure, but they are not walls in the traditional sense. They are softer, more elusive, more conceptual. It's also worth thinking about what this means for our place in the cosmos. We live inside a bubble defined by the speed of light and the age of the universe. Everything we know, every star we've catalogued, every galaxy we've photographed, lies within this bubble. Beyond it, there could be more of the same or something entirely different, but we can't reach it. Not now, not ever. That is our cosmic edge. Not because reality ends there, but because reality becomes unreachable. It's humbling to realize that the universe we experience is only a fraction of what exists, and that the rest is hidden behind the slow but relentless expansion of space. Now let's think about how expansion ties into the idea of time. If the universe is expanding, then in a sense time itself is tied to that expansion. The beginning of time coincides with the beginning of space. They are not separate things, but part of the same fabric. So when we ask whether the universe is finite, we're also asking whether time itself is finite. If space loops back on itself, does time? If space goes on forever, does time? If expansion accelerates, does time stretch in the same way? These are not questions with easy answers, but they remind us that space and time are inseparable. The edges of one are deeply connected to the edges of the other. Another fascinating aspect of expansion is that it changes the way we think about distance itself. In everyday life, distance is simple. You measure from one point to another, and that's that. But in cosmology, distance is elastic. A galaxy might be receding from us at faster than the speed of light, not because it's moving through space that quickly, but because space itself is expanding between us. In such cases, even though the galaxy exists, it is beyond our reach forever. That's another kind of edge, one that doesn't depend on walls or borders, but on the way reality itself behaves. To make this more concrete, picture an ant walking along a rubber band. If the rubber band stretches faster than the ant can walk, there will be points on the band the ant can never reach, no matter how long it walks. The stretching itself creates unreachable edges. That's what the expansion of the universe does on a cosmic scale. It creates regions forever beyond our grasp. not because they don't exist, but because the fabric between us is stretching too quickly. And once again, we find that edges are not just physical features, they're also consequences of laws and dynamics. They arise from the interplay of light, speed, expansion, and age. They are not things we stumble into, they are things that emerge from the rules of the cosmos itself. As you let this sink in, it's worth remembering that these ideas are not just theoretical musings, they're grounded in observations. We measure the redshift of galaxies, we map the cosmic microwave background, the faint afterglow of the Big Bang. We track the way galaxies move and how the universe expands. All of this points to a cosmos with horizons, with limits, with edges defined not by walls but by time and light. And yet, despite all of this, there is still room for wonder, because whether the universe is finite but unbounded, or infinite and stretching, we still face the same mystery. We live in a reality with edges of knowledge, and we are always pressed against them, peering outward, trying to imagine what lies beyond. Just as ancient sailors once stared at the sea and wondered what lay past the horizon, we stare at the cosmos and wonder what lies past our observable bubble. And perhaps, in doing so, we're already standing at the very edge of time itself. If we've already explored the way horizons in space can act as edges, the next natural step is to imagine what it would mean for time itself to present us with something like a wall. The very phrase can feel odd at first, because walls are things we picture in stone or steel, boundaries that block our path in space. Time doesn't seem to lend itself to such structures. Seconds slip past quietly, minutes follow, hours accumulate, and none of it feels as though it could slam into a barrier. Yet if we allow ourselves to picture it carefully, imagining a wall of time is a way to probe what we really mean by beginnings, endings, and limits. Think of how often we encounter walls in ordinary life. They stop us, redirect us, sometimes protect us. They force us to acknowledge that movement cannot go on forever in a given direction. If we translate this into the language of time, a wall would be the moment where before or after no longer applies. It wouldn't be made of bricks, it wouldn't have texture or colour, but it would be just as absolute, a boundary past which no experience, no event, no change could exist. The first example most of us can imagine is the beginning of time itself. The Big Bang, as described by modern cosmology, is often pictured as a wall at the far end of history. You trace events backward, galaxies drifting closer, stars unwinding into clouds of gas, particles merging into hotter and denser states, and eventually you reach a point where the equations break. That point is a kind of wall. The very notion of before becomes meaningless. You cannot ask what happened earlier because earlier is not a concept that applies. In that sense, the Big Bang is less an explosion and more a temporal boundary, a moment where time itself starts. It helps to use analogies here. Imagine a book. You flip back through the pages, each one filled with stories, events, memories. Eventually you reach the first page. You cannot go further back within the book because there is nothing printed before that. The beginning of time is like that first page. It's not that something was torn out, it's that the story simply starts there. A wall of time would be like the binding of the book itself, the place where the narrative begins, and the concept of before has no meaning within the story's framework. But beginnings aren't the only kind of wall we can imagine. What about endings? If the universe eventually grows cold and empty, with stars burning out and galaxies drifting apart, does time itself come to a halt? Cosmologists call this the heat death scenario. In it, the universe reaches a state of maximum entropy, where everything is so evenly spread that no new events can occur. No energy gradients remain to fuel processes. In such a state, change ceases. And if change ceases, then in some sense time ceases too, because time is defined by change. That would be another kind of wall, not one of fire and explosion, but one of silence and stillness. A wall where every tick of the clock stretches into nothingness, and eventually there is simply no more ticking at all. There are other endings we might imagine. A big crunch, for instance, where the expansion of the universe reverses and everything collapses inward, growing hotter and denser until it reaches a singularity. That too would be a wall of time, a moment when after no longer applies. Or a big rip where expansion accelerates so dramatically that galaxies, stars, planets, and eventually atoms themselves are torn apart. In that case, the wall would be more violent, but the principle is the same, a point beyond which no further moments exist. So we have at least two versions of walls already. The wall at the beginning, the Big Bang, and the wall at the end, whether it's heat death, crunch, or rip. Both are boundaries where the timeline stops. Both are conceptually absolute. But what makes them especially interesting is that they force us to confront how dependent we are on time itself. We cannot picture a before the beginning, or an after the end, without smuggling time back in. Our minds instinctively want to imagine something happening beyond the wall, but the very definition of the wall is that nothing can. It is a limit not just in physics, but in imagination. To explore this further, let's think about what it would feel like to encounter such a wall. Imagine you're walking down a hallway, each step representing a moment in time. Behind you are all the steps you've taken. Ahead of you, more hallway stretches out. Now picture reaching the end, where the corridor meets a solid barrier. You press your hand against it, and there is nothing beyond. That's the sensation a wall of time tries to capture. The steps stop, the corridor ends, and no matter how hard you try, you cannot move into a region that doesn't exist. But unlike a hallway, time's wall is not something you could physically touch. It would exist in the structure of reality itself. It's not that your body would collide with anything, it's that there would be no further now to arrive at. In everyday life, we never encounter this directly. Our personal experience of a wall of time comes only at birth and death. Before you were born, there were no moments for you. After you die, there will be no moments for you. These are personal boundaries in time, walls that define your individual experience. On the cosmic scale, the universe itself might have equivalent walls, not just for one life, but for all of existence. And here is where the idea becomes even stranger. Some scientists argue that time might not be infinite in the way we usually assume. It might be like a film reel with a definite number of frames. You can play it forward, frame by frame, but eventually the reel runs out. The movie ends, not because something is missing, but because the story is complete. In this analogy, the wall of time is like the end of the reel. You cannot keep watching, because there is nothing else to project. It's not that the projector broke, it's that the film itself has finished. Others take the analogy further. What if time loops back on itself? What if, upon reaching the end of the reel, it simply starts again from the beginning? In that case, the wall of time might not be absolute. It might be a doorway back into the first frame. That raises even more questions. Would the cycle repeat exactly, with every event unfolding the same way like a cosmic rerun? Or would it vary, creating slightly different versions each time? If so, the wall of time is less a dead end and more a reset button, marking the boundary between cycles. Another perspective comes from quantum physics. At extremely small scales, our usual ideas of space and time break down. Particles exist in superpositions, probabilities rather than definite states. Some physicists suggest that at these scales, time itself may not exist in the way we think it does. It may be emergent, arising only when systems become large and complex enough. If that's true, then the wall of time might be the point where this emergent property no longer holds. Beyond the wall, time might not end so much as dissolve, replaced by something more fundamental. That's harder to picture than a hallway or a reel of film, but it's a possibility many physicists take seriously. There's also the psychological dimension. For us as human beings, walls of time are felt in memory and anticipation. We cannot remember before birth, and we cannot anticipate after death. Those blanks are walls in our experience. Even during life, there are walls of sorts. Sleep erases our sense of continuous time. Anesthesia creates a gap in consciousness. These are small glimpses of what it means to bump against the edges of experience. They remind us that walls in time need not be cosmic in scale. They can appear in the simple interruptions of awareness, and yet, despite all these ways of picturing it, a wall of time remains elusive. We cannot observe it directly. We can only infer it from theory and from the limits of imagination. That makes it both unsettling and fascinating. It is unsettling because it suggests that everything we know is bounded. It is fascinating because it points to questions we have barely begun to answer. What does it mean for time to stop? What does it mean for reality if there is a before or an after that cannot exist? Perhaps the most useful way to think about it is this. A wall of time is not a thing in space. It is not located anywhere. It is a property of the timeline itself. It marks the edge of when, not of where. And that makes it unlike any wall we are familiar with. We can travel around a wall in space, but we cannot go around a wall in time, because the very act of going around requires time. The wall is absolute in a way few other things are. This leads to a final reflection. Imagining a wall of time forces us to confront our dependence on time as a concept. We live inside it the way a fish lives inside water. We don't notice it most of the time, we simply move through it, moment by moment. But when we imagine it having a wall, we realize how much of our thinking depends on the assumption that there will always be another moment. A wall of time is the scenario where that assumption fails, and by thinking about it, we learn not only about cosmology, but about ourselves, about the limits of our perception, our imagination, and our understanding. And so we can continue carrying this image of a wall of time with us, not as something final, not as something frightening, but as a way of sharpening our sense of what it means for time to have edges. Because from here, the question only deepens. If time has such walls, how do they shape the way we live inside it? And what metaphors might help us make sense of such a strange possibility? When we try to imagine something as abstract as a border in time, our minds often reach for metaphors. It is easier to picture the unknown by connecting it to something familiar. For time, two of the most powerful images are the river and the cliff. Both capture something essential about the way we experience moments passing, and both help us think about what it might mean for that passage to meet an edge. The river comes first, because it is the metaphor we use almost instinctively. Time feels like a current, always moving, carrying us forward whether we want to or not. We drift on it, sometimes smoothly, sometimes through rapids, but never backward. Every culture has described time this way at some point. We speak of time flowing. We speak of being swept along by events. We speak of hours washing over us like waves. It is a metaphor so natural that we rarely notice we're using it. If time is a river, then what would an edge be? One picture is the waterfall. The current carries you steadily until suddenly it meets a drop. The water plunges, and there is no further path along the surface. In this image, a wall of time is like the lip of the falls. You can drift only so far, and then the flow ends abruptly. Whatever lies beyond is unreachable, not because you stop moving, but because the river itself stops. It is a dramatic metaphor, but it fits the way we imagine beginnings and endings. The Big Bang could be pictured as the moment the river springs suddenly into existence from a hidden spring. The heat death could be pictured as the river thinning, slowing, and eventually evaporating into nothingness. Both are edges, seen through the language of water. But rivers also suggest continuity. Even when they branch, they still flow. They connect one place to another. They are never still for long. That makes the metaphor comforting in its own way. If time is a river, then perhaps its edges are simply different states of the flow. Perhaps at the source, the water bubbles up quietly, unformed. Perhaps at the end, it disperses into mist, no longer a channel but still part of the cycle of water. In that sense, the edges of time might not be abrupt cliffs, but transitions into something else. The river doesn't vanish, it changes form. Now let's turn to the cliff, the second metaphor. If the river suggests smoothness and continuity, the cliff suggests finality. It is the place where ground gives way to empty air. You walk, and then suddenly you cannot. You peer over the edge, and below is a drop into something unknown. For time, a cliff represents the idea of a hard stop, a moment where the timeline simply ends, and no more steps are possible. Birth can feel like this when you look backward. Death can feel like this when you look forward. The beginning and end of the universe can be pictured the same way. The cliff is where the corridor of time comes to a sudden halt. What makes the cliff metaphor powerful is that it emphasizes limits. You cannot keep walking. You cannot sidestep easily. You must confront the edge directly. In thinking about time, the cliff captures the unsettling idea that the universe itself might have a sharp boundary, beyond which the very concept of when ceases to apply. It is stark, uncompromising, and absolute. Of course, the river and the cliff are not mutually exclusive. They can work together, showing us different aspects of temporal edges. Time may feel like a river most of the way, smooth and steady, but at its boundaries it may resemble a cliff, dropping into mystery. The two images blend. The river flows until it meets the falls. The ground stretches until it reaches the precipice. Both convey the sense of motion meeting a limit. These metaphors also remind us of how much our imagination depends on familiar experiences. We cannot picture the end of time directly, so we borrow images from water and stone, from flow and terrain. Each metaphor captures something true, but each also has limits. A river eventually joins an ocean, but does time join something larger? A cliff drops into air, but what would time drop into? Here we see again the difficulty of using everyday concepts to describe something so fundamental. Still, the exercise is useful, because it helps us approach the question with more than just equations. It lets us feel it. Think about how these metaphors shape our language. When we say time flows, we're already picturing it as a river. When we say someone ran out of time, we're picturing a cliff, a sudden stop. These phrases guide how we think, even if we don't notice it. They colour our sense of what it means for time to have edges, and because language influences thought, these metaphors are not just poetic devices, they are tools that shape our intuition. Let's test the river image further. Imagine drifting down a wide, calm stream. The water carries you effortlessly. On either side, the banks slip by. You have no control over the current. It takes you forward whether you paddle or not. Now picture that current stopping. The water runs into a stone wall and has nowhere else to go. That image is strange, because in nature rivers don't end that way. They merge, they evaporate, they disperse. For a river to stop cold at a wall feels unnatural. That shows us the tension in the metaphor. Time as a river suggests continuity, but the idea of an edge suggests interruption. When we imagine a wall of time, we're imagining something a river can barely illustrate. Now test the cliff image. Imagine walking across open land, the horizon always ahead. You feel secure, the ground solid under your feet, then suddenly the earth drops away. A sheer precipice falls into mist. That moment, when your steps can go no further, captures the visceral sense of an edge. Yet in life, cliffs can often be walked around. They are obstacles in space, not absolutes. Time's edge, if it exists, would be more final. You cannot walk around it because there is no around without time to move in. That shows us the cliff metaphor is powerful but incomplete. It captures finality, but not the full strangeness of temporal borders. By holding both metaphors together, we begin to sense how unusual the concept really is. Rivers give us flow, continuity, emergence. Cliffs give us suddenness, absoluteness, endings. Time may contain both qualities. It may feel smooth in the middle, but at its boundaries it may end sharply. In that sense, the river and the cliff together offer a more complete picture than either one alone. And notice how, as we sit with these images, the question of time's edges becomes more tangible. It no longer feels like a purely abstract speculation. It feels grounded in experiences we know. Water slipping past, ground dropping away. These metaphors act like handholds on a slippery surface. They give us something to grip as we climb into ideas that otherwise resist visualization. The value of these metaphors also lies in how they connect the cosmic to the personal. A river reminds us of the flow of our own lives, carrying us from youth to old age. A cliff reminds us of the personal edge we all face at death. By projecting these experiences onto the universe, we gain an intuition about cosmic edges of time. The metaphors bridge scales, linking our small lives to the vastness of everything. Of course, we must always be cautious. Metaphors are guides, not truths. They illuminate certain aspects while hiding others. A river suggests inevitability, but time may not be inevitable in the same way. A cliff suggests abruptness, but time's edges may not be abrupt at all. Perhaps they are gradual, like twilight blending day into night. The danger is that we take the metaphor too literally. The usefulness lies in letting it carry us a little further into imagination, while remembering that reality may differ. Even so, metaphors are powerful precisely because they speak to intuition. Equations tell us about singularities, entropy, expansion. But metaphors let us feel what those words mean. They let us picture a life carried by a current or halted by a precipice. They make the strange more relatable, and in a topic as abstract as the edges of time, that relatability matters. It keeps us connected to the question, rather than lost in its abstraction. Let's carry these images with us. The river, with its flow and continuity. The cliff, with its finality and drop. Together they give us a language for the strange idea of temporal edges, and as we move forward, we'll see how these images help us understand not just beginnings and endings, but also the deeper question of what lies at the root of time itself. When people first began to wonder about the beginning of everything, they did not have telescopes or equations to guide them. They had only their observations of the sky, the rhythm of the seasons, and their own imagination. Many cultures developed stories in which time began with an act of creation, often involving gods, chaos, or some primordial void. These stories shared a common intuition, that time itself had to start somewhere. There had to be a first moment, even if that moment was described in mythic rather than scientific terms. Today, we approach the question differently, with the tools of physics and astronomy. Yet we find ourselves circling the same mystery. Was there truly a beginning of time? And if so, what does that boundary mean? The modern scientific answer starts with the Big Bang. It is not just a story about matter exploding outward into space. That image, though common, is misleading. The Big Bang was not an explosion in space. It was the expansion of space itself. It was the moment when the universe as we know it began to stretch, carrying energy and matter along with it. And most importantly for our question, it was the moment when time itself began. Before the Big Bang, according to standard cosmology, there was no before. Time is part of the fabric of the universe, and that fabric came into existence in that moment. To understand why scientists speak this way, we need to trace the evidence. The first clue came from the expansion of galaxies. When Edwin Hubble observed that distant galaxies were receding from us, and that the farther away they were, the faster they appeared to move, he was seeing the imprint of cosmic expansion. If the universe is expanding now, then in the past it must have been smaller, denser, hotter. Extrapolate far enough back and you reach a singular state of extreme density and temperature. That is the Big Bang. Not an explosion, but the starting point of expansion. The second clue came from the discovery of the cosmic microwave background radiation. In the 1960s, two radio engineers, Arno Penzias and Robert Wilson, accidentally stumbled upon a faint hum of microwave radiation coming equally from every direction in the sky. At first they thought it was interference, even going so far as to check whether pigeons nesting in their antenna might be responsible. But the hum persisted. Eventually it was recognised as the afterglow of the Big Bang, light released when the universe cooled enough for atoms to form, stretching into microwaves as space expanded. This discovery confirmed that the universe had a hot, dense beginning, lending strong support to the Big Bang model. The third clue comes from the abundance of light elements. The ratios of hydrogen, helium, and lithium observed in the cosmos match the predictions of nuclear processes that would have occurred in the first few minutes after the Big Bang. It's as though the early universe left behind a chemical signature of its birth. Put these lines of evidence together, and the picture is clear. The universe had a beginning. Space and time are not eternal in the past. They emerge from a singular boundary roughly 13.8 billion years ago. That boundary is what we mean when we say the Big Bang is the beginning of time. Now, what does that mean for our question about edges? If time began at the Big Bang, then it has a border at the past. You cannot ask what happened before, because the very concept of before is tied to time. Without time, before has no meaning. That's why physicists sometimes say it is meaningless to ask what came before the Big Bang. It's not that they are unwilling to speculate. It's that the question itself assumes a framework that doesn't exist beyond that boundary. Of course, this idea is difficult to grasp. Our minds are trained by experience to always think in terms of before and after. When we say the universe is 13.8 billion years old, it is natural to ask, yes, but what was happening 14 billion years ago? We want to extend the line backward indefinitely. But the Big Bang marks a point where the line itself begins. It is not a moment in time after another. It is the origin of time itself. Trying to picture what came before is like trying to picture a place north of the North Pole. The concept breaks down at the boundary. To make this more concrete, let's return to our earlier metaphors. If time is a river, then the Big Bang is the spring where the river bursts forth from the ground. You can walk upstream as far as you like, but eventually you reach the source. Beyond it, there is no riverbed. If time is a corridor, then the Big Bang is the doorway at the very start, the point where the hallway begins. You can trace your steps backward, but at some point you reach the threshold. Beyond it, there is no floor to walk on. This helps us feel the strangeness of the idea. We are so used to thinking of time as an endless backdrop that it is hard to accept it could have a boundary. Yet the evidence points strongly in that direction. Time is not infinite in the past. It has an edge, and that edge is the Big Bang. But there are other ways to think about it. Some physicists argue that the Big Bang may not have been the absolute beginning. Instead, it may mark the point where our current description of the universe begins to apply. Before that, there could have been something else, a different phase, a different state, a different kind of reality. In this view, the Big Bang is not the absolute start, but a transition. The wall of time is real for us, but it may not be absolute for the cosmos itself. For example, some theories suggest that the universe underwent a period of rapid inflation in its earliest fractions of a second, expanding faster than light. Others propose that our universe may have budded off from a larger multiverse, like a bubble forming in boiling water. In these scenarios, time might extend further back in ways we cannot access. The Big Bang would then be less like the first page of the book, and more like the beginning of a new chapter, with earlier pages hidden from view. Quantum gravity, the attempt to reconcile general relativity with quantum mechanics, also offers possibilities. Some models suggest that time might not have a singular beginning, but instead emerge smoothly from a quantum state where ordinary notions of time do not apply. In such a picture, the Big Bang is a boundary not because time truly stops, but because our classical understanding of time ceases to be meaningful. Beyond that, something else exists, but we lack the language to describe it. Whether absolute or transitional, the Big Bang functions as a temporal edge for us. It marks the point beyond which we cannot currently see, calculate, or imagine with confidence. It is our cosmic horizon in the past. Just as the observable universe defines the edge of what we can see in space, the Big Bang defines the edge of what we can know in time. And there is something profoundly humbling about that. Every clock that ticks, every calendar that turns, every life that unfolds is part of a timeline that began at that boundary. We are inhabitants of a universe with a birth date. We measure our days against a cosmic clock that started 13.8 billion years ago. That awareness ties us to the cosmos in a direct way. We are not outside of it, observing from a distance. We're inside its timeline, carried along from its beginning. Thinking of the Big Bang as a temporal boundary also reshapes how we think about origins in general. It reminds us that not all beginnings are like stories with a cause and an effect. Some beginnings are absolute, the point at which concepts like cause and before lose their meaning. That is difficult for the human mind to accept, but it is a truth science has slowly uncovered. And yet, even as we acknowledge this, we can't help but wonder, is it really the beginning, or is it just the edge of our knowledge? Will future theories reveal something beyond, just as new maps once revealed lands beyond the horizon? That curiosity keeps the question alive. The Big Bang is both an answer and an invitation. It is the edge of time as we know it, and at the same time a doorway to questions we have only begun to ask. If there was a boundary at the beginning, is there another waiting at the end? Does time stretch forward indefinitely, or does it too meet a wall? If we accept that the universe had a beginning, it's natural to ask whether it will also have an end. The symmetry of the thought is compelling. If there was a first moment, why not a last? We look at birth and death in our own lives, at the cycles in nature, at stories that have beginnings, middles, and endings. And it feels almost inevitable that the universe itself should also have a final chapter. The question is not just whether time extends infinitely forward, but whether it might eventually meet another boundary, another wall beyond which there is no after. The most well-known scenario for the universe's end is called heat death. It sounds dramatic, but the idea is simple. The universe is governed by the second law of thermodynamics, which says that entropy, a measure of disorder, tends to increase over time. Systems evolve from ordered states into disordered ones, from usable energy into unusable heat. This law applies not just to engines and ice cubes, but to the universe as a whole. Over billions and trillions of years, stars will exhaust their fuel, galaxies will dim, matter will spread thinner and thinner. Eventually, everything will reach a state of maximum entropy, where energy is evenly distributed and no further change is possible. In that state, no stars burn, no galaxies shine, no processes occur. The universe does not end in fire, but in stillness. Time itself becomes strange here. If nothing changes, if no events occur, then time loses its meaning. A second is defined by the ticking of a clock, but in a universe without processes, without clocks, without motion, what does a second even mean? Heat death is therefore not just the end of activity, it is, in a profound sense, the end of time as we understand it. The river has slowed to a standstill, the cliff has been reached, and all that remains is silence. But heat death is only one possibility, another is the big crunch. In this scenario, the expansion of the universe does not continue forever. Instead, it slows, stops, and reverses. Galaxies draw back together, stars collapse inward, the universe shrinks rather than stretches. Eventually, all matter and energy would be compressed back into a singular state, similar to the conditions of the Big Bang. Time itself would collapse along with space, reaching an endpoint where after no longer exists. The Big Crunch would be a mirror image of the Big Bang, a closing bookend to match the opening one. For much of the 20th century, scientists debated which of these two fates was more likely. Would the universe expand forever into heat death, or collapse back into a crunch? The answer seemed to depend on how much matter the universe contained. If there was enough mass, gravity would eventually halt the expansion and pull everything back. If not, expansion would continue unchecked. Observations of galaxies, clusters, and the cosmic microwave background were all attempts to weigh the cosmos to see which way it would tilt. Then, in the late 1990s, a discovery shifted the debate. Teams studying distant supernovae found that the universe's expansion was not slowing down, but speeding up. Something, later called dark energy, was pushing galaxies apart with increasing force. This suggested a new possibility: the Big Rip. In this scenario, acceleration continues to grow until it overwhelms all forces. Galaxies are torn apart, stars are pulled from their systems, planets from their orbits, atoms from their nuclei. Even the fabric of space itself could rip apart. The end is not a quiet heat death or a collapsing crunch, but a violent unravelling. The Big Rip is speculative, and it depends on the exact nature of dark energy, which we still do not understand. But it shows how many different kinds of walls time might encounter. One is a gradual fade into stillness, another is a collapse into density, another is a catastrophic tearing. Each represents an edge of time in a different form, but all carry the same message, that the timeline may not stretch forward forever. And then there are stranger possibilities still. Some theories of quantum gravity suggest that the universe may bounce rather than end. Instead of a big crunch terminating time, the collapse could lead to another expansion, creating a cycle of universes. Time would have edges, but they would loop back into beginnings. The wall would also be a doorway. In this view, our universe might not be a singular story, but one in an infinite sequence, each with its own birth and death. Others suggest that the universe could tunnel into a different state altogether. In quantum mechanics, systems can shift between states in ways that defy classical intuition. The vacuum of space itself may not be perfectly stable. It could decay into a lower energy state, releasing immense energy in the process. If that happened, it would rewrite the laws of physics in an instant, creating a new universe inside the old one. From our perspective, time would meet a sudden wall, replaced by a new kind of reality. These possibilities remind us that when we talk about the end of time, we are really talking about the limits of our theories. Heat death comes from thermodynamics. The Big Crunch comes from gravity. The Big Rip comes from dark energy. Quantum bounces and vacuum decay come from quantum mechanics. Each framework gives us a different edge, a different wall, a different way time might run out. The variety is dizzying, but it is also telling. It shows us that the end of time is not a settled question. It is a horizon in science, a place where speculation and evidence meet in uneasy balance. It's also worth thinking about how these cosmic endings echo in our personal sense of time. Heat death resonates with the idea of aging, of gradual decline into stillness. The Big Crunch resonates with the idea of collapse, of being drawn back into origins. The Big Rip resonates with the idea of catastrophe, of sudden disintegration. In each case, we project the cosmic onto the personal, and the personal onto the cosmic. The end of the universe becomes a metaphor for the edges we face in our own lives. And here is a curious point. Even if the universe ends in one of these ways, what happens to time afterward may not be a question we can even frame. If there is no activity, no change, no observers, then time itself may simply not exist. It would not be a matter of endless emptiness stretching forward, but of no forward at all. Our minds struggle to grasp this because we instinctively imagine nothing as a kind of empty time. But true nothingness, if it exists, may lack time altogether. That is what makes the idea of an end so difficult. It is not just the end of events, but the end of the framework in which events occur. At the same time, the universe continues to surprise us. Every major step in cosmology has revealed something unexpected. Expansion itself, dark matter, dark energy. It may be that the ultimate fate of the universe is something we have not yet imagined, something stranger than heat death, crunch, rip, or bounce. Perhaps time does not end at all but transforms into something we cannot yet describe. Perhaps the wall is not a wall, but a transition. For now, though, the important thing is that the universe does not appear to be eternal in any simple sense. Whether by fading, collapsing, ripping, or transforming, it may one day meet a boundary. That boundary, whatever form it takes, would be the far edge of time. Just as the Big Bang marks the beginning, so the universe's end marks the limit of the future. Between them stretches the span of history from the first atoms to the last stars. We live somewhere in the middle, looking back toward the boundary behind us and forward toward the one ahead. And this thought, while immense, is not something to fear. It is simply the shape of reality as we currently understand it. Edges do not diminish what lies between them. They frame it, give it context, help us understand its scale. The universe's edges, whether in the past or the future, remind us of the fragility and preciousness of the present moment. They tell us that time is not just an endless expanse, but a story with contours, with boundaries, with meaning. And so, from beginnings to endings, from Big Bang to heat death, from walls to horizons, we trace the arc of time. Each possibility adds depth to the picture, each theory adds texture to the question. And as we continue, we can turn to another puzzle. Why does time move forward at all? Why does it have an arrow pointing from past to future, instead of flowing equally in both directions? That too may hold clues to the edges of time. Every day we live with a simple fact that feels so obvious we rarely stop to question it. Time moves forward. It doesn't pause, it doesn't reverse, it doesn't skip backward like a scratched record. Morning becomes afternoon, afternoon becomes night. The days add up into months and years. Broken glass doesn't leap back onto the table and reassemble itself into a cup. Smoke doesn't return to the fire and become wood again. We feel this directionality everywhere in life, and we take it for granted. But when scientists began to think carefully about it, they realized something surprising. Most of the fundamental laws of physics do not care about direction. They work equally well forward and backward. Equations describing how particles move, how planets orbit, how light travels, all of these are symmetrical in time. If you reversed them, they would still make sense. Yet the world we live in is not symmetrical. It is deeply directional. There is an arrow pointing from past to future. The puzzle is why. This puzzle matters for our question about time's edges. If time has boundaries, those boundaries may be tied to its direction. The arrow of time seems to emerge from conditions at the beginning of the universe. The Big Bang set the initial conditions, and from them the arrow emerged. So understanding why time points forward may help us understand why it might eventually stop or meet an edge. One of the main explanations comes from entropy. The second law of thermodynamics tells us that entropy tends to increase. Systems evolve from ordered states to disordered ones, from usable energy to unusable energy. Think of a deck of cards shuffled randomly. It is far more likely to end up in a messy order than in a perfectly sorted one. Think of cream poured into coffee. It naturally mixes into swirls and eventually blends completely, never spontaneously separating again. Entropy gives us a measure of this tendency, and it defines a direction. That direction is what we call the arrow of time. The connection between entropy and time can be seen everywhere. Ice cubes melt in warm water, but warm water doesn't spontaneously form ice cubes. Heat flows from hot to cold, but not the reverse. Your body ages, cells accumulate damage, systems break down. None of these processes run backward. They all share a common tendency toward greater disorder. It's not that the laws of physics forbid reversals in principle. It's that reversals are so improbable as to be practically impossible. Entropy ensures that the forward direction is overwhelmingly more likely. This raises a deeper question. If entropy drives the arrow of time, why was the universe ever in a low entropy state to begin with? The Big Bang was not only the beginning of time, it was also an extraordinarily ordered state. Matter and energy were distributed in ways that allowed complexity to emerge. From that low entropy beginning, entropy has been increasing ever since, giving rise to the arrow. Without that starting condition, there might be no arrow at all. Some physicists argue that the true mystery of time is not why entropy increases, but why the universe began so ordered in the first place. Another perspective comes from cosmology. As the universe expands, entropy increases. Stars burn fuel, galaxies form and evolve, structures emerge. Expansion gives entropy room to grow, ensuring that the arrow continues to point forward. If the universe one day contracts, as in the Big Crunch scenario, some theories suggest entropy might decrease, reversing the arrow. That would mean time itself could appear to run backward near the end. Others disagree, arguing that entropy would still increase regardless. The debate shows how closely tied the arrow is to the fate of the universe. There are also local arrows of time tied to specific processes. The thermodynamic arrow is one. The cosmological arrow tied to expansion is another. The psychological arrow is yet another, defined by memory. We remember the past but not the future. Our brains store records of what has happened, but not of what will happen. This gives our experience of time a direction, even if the underlying physics doesn't require it. The radiative arrow is another. Waves of light and sound spread outward from sources, not inward. All these arrows align, reinforcing our sense that time has a single direction. But the fact remains, the equations themselves are mostly reversible. Newton's laws, Maxwell's equations, even much of quantum mechanics, all of them work equally well in reverse. Only when you bring in entropy, measurement, or observation does direction emerge. That means the arrow of time is not built into the fundamental rules, but arises from conditions and probabilities. It is an emergent property of the universe, not a law written into its foundation. This realization can feel unsettling. We are so used to thinking of time's direction as absolute that it's strange to think of it as contingent, dependent on initial conditions. But it also deepens the mystery of edges. If the arrow emerged at the Big Bang, perhaps it will dissolve at some future boundary. If entropy reaches a maximum in heat death, the arrow may vanish, leaving a timeless state. If the universe collapses, the arrow might reverse. Each edge we considered earlier ties directly into the fate of the arrow. To bring this closer to home, consider the role of memory. We know the past because traces of it remain. Fossils record ancient creatures. Photographs capture moments. Neural pathways in our brains store events. These are physical records, and they depend on entropy. It is easier to create records than to erase them. Smoke leaves traces in the air. Rebuilding wood from smoke would require impossible coordination. Because records accumulate, we know the past, but not the future. That asymmetry is part of the arrow. It shapes our entire experience of living. Without it, time would feel very different. Some scientists even argue that consciousness itself is tied to the arrow of time. Our sense of continuity, of being carried forward, depends on memory and anticipation. Without the arrow, experience as we know it might not exist. That means that asking whether time could have an edge is not just about physics, but about what it means for beings like us to exist at all. If time lost its arrow, could we still perceive it? Could we still be? There are also thought experiments that test the arrow. Imagine a universe where entropy decreases. Broken cups leap back together. Smoke gathers and compresses into logs. People grow younger. In principle, the laws of physics could allow this, but in practice it is so staggeringly improbable that it never occurs. Such a universe would feel alien. Memory would point the other way. The future would be the direction of order, the past the direction of disorder. Even the very language of before and after might lose its meaning. This shows us how deeply the arrow is woven into our experience. It is not just about physics, it is about the very structure of life. Without it, causality collapses, stories cannot be told, actions lose coherence, the arrow gives us sequence, progression, narrative. It is what makes edges meaningful in the first place. Without direction, a beginning and an end would blur together. The Big Bang and heat death would lose their distinct roles. Time would be shapeless, and so the arrow, though emergent, is fundamental to how we live inside time. It ties us to the universe's beginning, because that low entropy state is what gave the arrow its start. It ties us to the universe's end, because that high entropy state is where the arrow may dissolve. It ties us to every moment in between, because memory, causality, and experience depend on it. Thinking about this slowly, we realize that the arrow of time may itself be a kind of horizon. It is not an edge in the sense of a wall, but it is a boundary on how we experience reality. We can only move forward, never back. We can only accumulate records, never erase them. That unidirectional quality defines our entire sense of existence. It is not a physical wall, but a psychological and thermodynamic one. It shapes the edges of our lives just as much as any cosmic boundary shapes the universe. As we continue to trace the mystery of time's borders, we carry the arrow with us. It explains why we can talk about beginnings and endings at all. It explains why edges make sense in the first place, and it hints that, at the deepest level, time's edges and time's arrow may be one and the same. It's easy to take the flow of time for granted. From the moment we wake in the morning until the moment we drift into sleep again, time seems to move without interruption. The clock ticks, the sun rises and sets, our thoughts string themselves into sequences. Even when we try to imagine time standing still, our minds tend to picture it as a frozen moment that still somehow exists in time, a pause in the movie rather than the disappearance of the film reel. But what would it really mean if time itself stopped flowing, not just for us as individuals but for the universe as a whole? The first way to think about this is simple. Without the flow of time, change would stop. Change is the measure by which we know time exists. A cup falls and breaks, a candle burns lower, clouds drift across the sky. These are changes, and time is the framework that allows us to order them. If time were to stop flowing, all change would vanish. The cup would hang forever mid-fall. The flame would remain fixed, neither shrinking nor growing. The clouds would freeze in place. The entire universe would become a single still frame, like a photograph that never develops further. But here's the strange part. If no change occurred, would there be any way to notice that time had stopped? Think about it carefully. To observe the halt of time, you would need a before and after, a memory of things moving, and then a recognition that they had ceased. But without time, you cannot form that comparison. Consciousness itself requires change, the firing of neurons, the sequence of thoughts. If those freeze as well, then no one could ever experience the stoppage of time. From the inside, it would be indistinguishable from not existing at all. This makes the question tricky. To say that time has stopped may not be something we can even describe coherently. It might be like trying to imagine a colour we've never seen, or a shape with more sides than geometry allows. Our language and thought are steeped in temporal flow. To remove it is to remove the very framework in which we think. Still, we can explore the idea by looking at physical theories. In relativity, time is not absolute, but tied to motion and gravity. Clocks tick differently depending on how fast they move or how close they are to a massive body. Near the event horizon of a black hole, time for an outside observer appears to slow to a crawl. A person falling in would not notice their own time slowing, but to someone watching from a distance they would appear to freeze, suspended forever at the edge. In this sense, physics already gives us examples of time flowing differently in different frames. What would it mean if, in some ultimate sense, time ceased altogether? It would be like extending the black hole horizon to the entire universe, freezing everything in place from every perspective. Quantum mechanics adds another wrinkle. Some interpretations suggest that time is not fundamental at all, but emerges from correlations between events. In this view, if those correlations stopped, time itself would vanish. That doesn't mean the universe would become a frozen picture. It means the very concept of picture and frozen would lose their meaning. Without time, there is no sequence, no succession, no was or will be. There is only a timeless state, something we can't picture, because picturing requires a sequence of thoughts. Philosophers have also wrestled with this. Some argue that time is an illusion created by our minds, a way of organizing sensory input. If that's true, then the stoppage of time might simply mean the collapse of that illusion. The universe could exist in a timeless reality, with our perception of flow being a construction layered on top. In that case, asking what happens if time stops is like asking what happens if a mirage disappears. What remains is whatever was always there, independent of the illusion. But for us, the question feels more immediate. What would happen to a person if time stopped? Could they feel themselves frozen? Could they be aware of it? The answer appears to be no. Awareness requires a sequence. To be aware of being frozen is to not be frozen. So from a subjective standpoint, the stoppage of time is indistinguishable from ceasing to exist. It is not something that could be lived through. It is, in a sense, the ultimate edge. This connects to the earlier discussion of heat death. In a universe where nothing changes, time loses its meaning. It's not that time continues, but emptily. It's that the very framework dissolves. That is what we mean by time stopping. It is not a frozen moment within time. It is the absence of moments altogether. Now consider the psychological edges we encounter in our own lives. Sleep is one. When you fall into deep, dreamless sleep, hours can pass without any sense of them. You close your eyes, and the next thing you know, it's morning. Consciousness provides no record of the intervening time. In a way, it's a tiny taste of timelessness, though the world continues moving around you. Anesthesia is another. People who undergo surgery often describe the time under anesthesia as a blank instant. One moment they are counting backward, the next they are waking up in recovery. Hours may have passed, but their experience contains no trace of them. These are not true halts of time, of course. They are halts of consciousness. But they show us how, subjectively, the absence of time feels like nothing at all. Death, too, can be thought of in this way. From the outside, it is a process, a cessation of biological functions. From the inside, it is likely indistinguishable from timelessness. There is no awareness of being outside time, no perception of the absence. To die is, in this sense, to reach a personal edge of time, beyond which the very notion of experience vanishes. All of these examples highlight the difficulty of the question. Time stopping is not like a machine breaking down, where you could step outside and fix it. It is more fundamental than that. If time stopped, there would be no outside to step into. There would be no sequence in which to notice or respond. That's why scientists and philosophers often struggle to articulate it. It is not just unimaginable. It may be logically incoherent in the way we frame it. Still, the exercise is valuable because it forces us to examine how deeply our world is tied to the flow of time. It shows us that what we call time is not just a neutral backdrop, but the very condition for change, awareness, and existence. Asking what happens if time stops is another way of asking what time really is. And by probing that, we move closer to understanding whether it might truly have edges. One interesting possibility is that time may not stop everywhere at once. In relativity, time can flow differently in different regions. Perhaps at some extreme edge of the universe, time slows and halts, while in other regions it continues. This idea is speculative, but it suggests that the stoppage of time need not be absolute. It could be relative, tied to conditions of gravity, energy, or geometry. In that case, the edge of time might be more like a boundary region than a universal freeze. Another possibility is that time doesn't stop, but transitions into something else. Just as water turns to ice, perhaps time turns into another kind of dimension we cannot yet imagine. In that case, what feels to us like a halt may actually be a transformation. Time does not end, but changes character. The flow we are familiar with may dissolve, replaced by something beyond our current perception. For now, we cannot know which, if any, of these scenarios is real. But even in uncertainty, the question serves a purpose. It reminds us of the fragility of the assumptions we live by. It reminds us that time, so constant and familiar, may not be as absolute as it feels. And it prepares us to think more deeply about what happens at the true edges of reality, where our understanding stops and something stranger begins. When Einstein developed the theory of relativity in the early 20th century, he changed forever the way we think about time. Before relativity, time was seen as something absolute, a universal stage that ticked the same everywhere, for everyone. Seconds were thought to be identical whether you were on Earth or travelling among the stars. Clocks, it was assumed, simply measured the steady rhythm of the universe. But relativity showed that this picture was wrong. Time is not absolute. It is flexible, elastic, and deeply intertwined with space and motion. And nowhere is this more striking than near horizons and black holes, where time itself seems to warp, slow, or even come to a standstill. The key idea in relativity is that space and time are not separate. They form a single fabric called space-time. Events happen not just in space, not just in time, but in space-time. And that fabric can bend under the influence of matter and energy. Just as a heavy ball placed on a trampoline causes the surface to sag, mass and energy cause space-time to curve. Objects then move along the curves of this fabric, and what we experience as gravity is really just the effect of that curvature. One consequence of this curvature is that time does not flow at the same rate everywhere. A clock closer to a massive object will tick more slowly than a clock farther away. This is called gravitational time dilation. It has been measured in laboratories on Earth, where clocks a few meters apart, one closer to the ground than the other, tick at slightly different rates. It has been confirmed by satellites, where clocks orbiting Earth run a bit faster than clocks on the surface because they are farther from Earth's gravity. Without adjusting for this effect, GPS technology would quickly drift out of accuracy. Relativity is not just a strange theory. It is something we use every day, even if we don't notice. But the effect becomes more dramatic near very massive objects. Imagine approaching a black hole. From your perspective, as you fall in, time feels normal. Your watch ticks steadily, your heartbeat continues, your thoughts flow as usual. But to an outside observer watching from far away, your time appears to slow. As you near the event horizon, the boundary beyond which nothing can escape, the slowing becomes extreme. To the distant observer, you appear to freeze at the edge, never quite crossing. Light from you becomes redder and dimmer, stretched by gravity until it fades away. From the outside, it seems as though you have been suspended forever on the threshold. This creates a strange paradox of perspectives. For you, time continues normally as you fall past the horizon. You cross it without noticing anything special, and you continue toward the singularity at the centre. But for the observer outside, your time has slowed to a halt at the edge. Both perspectives are valid within relativity. There is no single, true flow of time. Each observer experiences their own, and both are consistent with the laws of physics. Time is not one thing, it is relative, shaped by motion and gravity. This relativity of time challenges our intuition. We tend to think of time as universal, shared by everyone, but relativity shows that there is no single cosmic clock. There are only local clocks, each ticking at its own rate, each tied to the curvature of space-time around it. This means that time itself has warps and folds, not just space. And those warps can be so extreme near black holes that they become like edges, horizons beyond which events cannot be seen or influenced. These horizons are not limited to black holes. The universe itself has a horizon, set by the speed of light and the expansion of space. Just as an event horizon hides what happens inside a black hole, the cosmic horizon hides regions of the universe beyond which light has not yet reached us. In both cases, time and space are bounded not by walls but by limits of causality. You cannot receive information from beyond a horizon because light and signals cannot cross. In this way, relativity creates natural edges, not physical barriers, but horizons defined by the structure of space-time itself. It's worth pausing here to consider how radical this is. In Newton's picture, time was absolute, the same everywhere. In Einstein's picture, time depends on where you are, how fast you are moving, and how much gravity surrounds you. In the most extreme cases, it can appear to stop from one perspective while continuing from another. The very idea of a single shared timeline dissolves. Instead, the universe contains countless local times, each bound to its own region of space-time. This makes us rethink what it means for time to have an edge. An edge might not mean a universal stop. It might mean that in some regions time slows, halts, or bends in ways inaccessible to others. Horizons create edges of experience, where one observer cannot see what another experiences. For the person falling into a black hole, time continues. For the observer outside, time ends at the horizon. The edge is real, but it is relative. Relativity also reveals another kind of time dilation, tied to motion. When objects move close to the speed of light, their time slows relative to stationary observers. This has also been measured in experiments. Particles moving at near light speeds live longer than they would at rest, because their internal clocks tick more slowly. Astronauts travelling fast would age less than those on Earth, though the effect at current speeds is tiny. In principle, if you travel close enough to light speed, you could cross centuries in what felt like a few years. For you, time would flow normally. For others, you would appear to have leapt into the future. This means that time is not only warped by gravity, but also by velocity. In relativity, both effects are part of the same fabric. Whether near a massive object or moving close to light speed, time is flexible. It stretches and compresses, always relative to the observer. Again, this challenges the notion of time as a universal flow. Instead, it is a local phenomenon, shaped by the conditions of space-time. Black holes remain the most dramatic example. The event horizon is not just a place in space, it is a boundary in time. From the outside, it is the edge beyond which future events cannot affect us. From the inside, it is the edge of no return. Time and space exchange roles in strange ways. Distances become times, times become distances. The singularity at the centre represents the ultimate breakdown of our equations, the place where curvature becomes infinite and our understanding stops. It is the sharpest example of an edge in time and space combined. But the importance of relativity is not only in these exotic places, it is also in the way it shows that time is not fundamental in the way we once thought. If time can slow, if it can stretch, if it can differ for different observers, then it is not the rigid backdrop we once assumed. It is part of the fabric of the universe, woven with space and subject to bending and warping. That means its edges too may be more complex than we can easily imagine. They may not be universal walls, but horizons and distortions relative to perspective. And here is where relativity touches something profound. It shows that our ordinary sense of time, the ticking clock and the flowing seconds, is only an approximation, valid in our local conditions. Beyond those conditions, near black holes, at near-light speeds or at cosmic scales, time behaves differently. To ask whether time has an edge is to ask about these extreme conditions where relativity shows us that our intuitions break down. This realization prepares us to explore even deeper puzzles. If relativity warps time near horizons and black holes, what happens at the smallest scales, in the realm of quantum mechanics? Relativity showed us that time bends and stretches in the presence of mass, motion and horizons. But when we try to look even closer, to the very smallest scales of reality, relativity alone is not enough. At those scales, the world is ruled by quantum mechanics, and here the picture of time grows even stranger. the neat flow we take for granted in daily life, the steady ticking we imagine in our minds, seems to dissolve into probabilities, uncertainties, and questions we cannot yet answer. It is here, at the quantum level, that we begin to wonder whether time itself might break down. To see why, we need to recall what quantum mechanics is about. In the classical world, objects have definite properties. A ball is here, moving at this speed, along that path. In the quantum world, particles do not behave so neatly. They exist in superpositions, occupying many possible states at once until observed. An electron can be in multiple places. A photon can travel multiple paths, and only when we measure them do we get a definite outcome. This strange behaviour has been confirmed in countless experiments, from the double-slit experiment to quantum entanglement. It is not an illusion. It is the fundamental way the microscopic world behaves. But time in quantum mechanics is treated differently than space. Space is represented by operators, mathematical objects that can be uncertain and probabilistic. A particle's position is not definite until measured. Time, on the other hand, is usually treated as a parameter, an external backdrop against which events unfold. That means quantum mechanics takes time as something absolute, even as it makes space fuzzy. This asymmetry has always been puzzling. If space is uncertain, why should time be fixed? And if relativity tells us that space and time are part of the same fabric, why should quantum mechanics treat them differently? This mismatch becomes especially troubling when we try to unite relativity and quantum mechanics. At large scales, relativity works beautifully. At small scales, quantum mechanics works beautifully. But at scales where both gravity and quantum effects matter, such as near singularities, or at the Planck scale, our theories clash. Relativity treats space-time as smooth and continuous, bending under mass and energy. Quantum mechanics suggests the world is granular, probabilistic, and uncertain. Put the two together, and space-time itself may become quantized, fluctuating, jittering, no longer smooth. At that level, time as a steady flow may cease to make sense. The Planck scale gives us a way to picture this. Named after Max Planck, it is the scale where quantum effects of gravity are thought to dominate. The Planck length is unimaginably small, about 10⁻⁵ meters. The Planck time is equally tiny, about 10⁻⁴ seconds. Below these scales, our current theories cannot describe what happens. It is possible that space-time itself breaks down into a foamy, fluctuating structure. If that is true, then time does not flow continuously at the smallest scales. It may emerge only as an approximation, valid when averaged over larger scales. Think of a digital image. From a distance, it looks like a smooth picture. Up close, you see pixels. Perhaps time is like that. From our perspective, it feels smooth and continuous. But at the smaller scales, it may be pixelated, grainy, composed of indivisible units. If so, the flow of time is not fundamental. It is an emergent illusion created by countless microscopic processes. There are hints of this idea in various approaches to quantum gravity. Loop quantum gravity, for example, suggests that space-time itself is made of discrete loops. Time would not be continuous but quantized, arising from the evolution of these loops. String theory, another approach, envisions tiny vibrating strings as the fundamental entities. Space-time, including time, may emerge from their dynamics, not exist independently. In both views, time is not a given. It is something that appears only at scales large enough for smoothness to emerge. Another quantum puzzle is the role of measurement. In quantum mechanics, a system evolves smoothly according to the Schrödinger equation, until measured. At that moment, the wave function collapses into a definite outcome. This collapse introduces an asymmetry in time. Before measurement, the system evolves reversibly. After measurement, it snaps into place irreversibly. The very act of observation introduces a kind of arrow of time into quantum mechanics. But what exactly counts as a measurement, and why should observation have this effect? These are still open questions, and they touch directly on the nature of time. Quantum entanglement deepens the puzzle. When particles are entangled, measuring one instantly determines the state of the other, no matter how far apart they are. This seems to defy the limits of space and time, creating connections that transcend distance. Experiments confirm that entanglement is real, though it cannot be used to send signals faster than light. Still, it suggests that our ordinary notions of time and causality may not be the whole story. If events can be correlated instantly across vast distances, perhaps time itself is not as fundamental as we assume. Some interpretations of quantum mechanics even suggest that time may not exist at the most fundamental level. The Wheeler-DeWitt equation, an attempt to merge quantum mechanics with general relativity, famously contains no explicit time variable. It describes the universe as a timeless state. In this picture, what we experience as time is a derived concept, emerging from correlations between parts of the system. Time is not something the universe has. It is something we perceive because of the way events relate to one another. This idea is radical, but it has support from several directions. If time is emergent, then asking whether it has an edge may be like asking whether temperature has an edge. Temperature does not exist at the level of individual particles. It emerges only when you consider many particles together. In the same way, time may not exist at the smallest scales. It may emerge only when enough complexity arises. In that case, the edges of time are not physical boundaries but conditions where emergence fails. This also changes how we think about the beginning of the universe. If time is emergent, then the Big Bang may not have been the absolute beginning. It may have been the point where time as we know it crystallized out of a timeless state. The edge of time would then be less like a wall and more like a phase transition. Before it, reality may have existed in a timeless form, beyond our comprehension. After it, time emerged as a property of that reality, giving rise to sequences, causality, and history. And what about the far future? If time is emergent, then in a heat-death scenario, when the universe is uniform and featureless, time may dissolve again. With no events to mark succession, no gradients to drive change, time may simply fade out. In this sense, both the beginning and the end of time could be places where time ceases to exist, not because it has been destroyed, but because the conditions for its emergence no longer hold. All of this shows how fragile our everyday concept of time is. We think of it as a river, steady and universal, but quantum puzzles suggest it may be nothing of the kind. It may be a shadow cast by deeper processes, an approximation valid at human scales, but breaking down at the smallest scales of reality. That is why the edges of time are so difficult to define. They are not necessarily physical boundaries. They may be conceptual ones, places where our familiar picture no longer applies. And yet, despite the strangeness, these ideas connect back to our own experience. Think of how memory creates a sense of flow. Think of how observation creates outcomes. Think of how probabilities collapse into definites when we make choices. All of these echo the quantum world. They remind us that time is not just a background we move through. It is intertwined with observation, with experience, with the way reality unfolds. If time breaks down at small scales, then perhaps our sense of flow is the large-scale illusion, built from countless quantum events stitched together into continuity. This thought brings us back to the edges we have been following. Relativity gave us horizons, where time slows and bends. Quantum mechanics gives us scales where time dissolves, where flow may be emergent rather than fundamental. Both point to the same conclusion. Time is not simple, not absolute, not guaranteed. It is fragile, dependent, contingent, and that fragility is what makes its possible edges so fascinating. As we sit with the strangeness of quantum puzzles, we are left with a question that is as much about perception as about physics. If time can dissolve at small scales, If it can emerge and vanish depending on conditions, then what does that mean for us, creatures who live entirely within its flow? When we think about the edges of time, it's easy to focus only on physics, the Big Bang, black holes, quantum scales, horizons of the universe. But there is another domain where time shows its limits, one that is closer to us and just as mysterious. That domain is the mind. The way we experience time is not only shaped by clocks and cosmic laws, it is shaped by memory, by perception, and by forgetting. For us as human beings, time has psychological borders as real as any horizon in space. Start with memory. We know the past because we remember it. Memory gives us a record of what has already happened, a trail of evidence that builds a sense of continuity. Without it, the past would dissolve into nothingness. Imagine waking up each morning with no recollection of yesterday. Life would feel like a series of disconnected flashes with no thread linking them. It is memory that stretches those flashes into a line. It turns the present moment into part of a story, one that includes both what has been and what is coming. But memory has limits. No one remembers everything. Our minds record selectively, holding on to certain moments and letting others slip away. Some memories are vivid, etched deeply, replayed again and again. Others fade quickly, disappearing almost as soon as they arrive. This creates edges in our personal timeline. We can recall childhood to some degree, but not before it. We can replay certain events, but not others. The borders of memory are borders of time, defining where our personal history begins and where it is lost. Think about early childhood. Most people have what psychologists call childhood amnesia. Memories before the age of 3 or 4 are almost always absent. Our lives did not begin then, but our ability to remember them did not yet exist. The time before those memories is like a blank region of the map. It is a personal version of the Big Bang, a beginning of remembered time. Everything earlier is hidden, not because it didn't happen, but because we cannot access it. At the other end lies forgetting. Memories can fade over years, becoming hazy or distorted. Some vanish entirely, leaving only fragments behind. Others may be overwritten by later experiences, reshaped by retelling, or altered unconsciously. Forgetting creates soft edges in the past, where clarity dissolves into vagueness. Just as the universe has horizons beyond which light cannot reach us, our minds have horizons beyond which memories cannot be retrieved. These horizons shape our personal sense of time just as much as cosmological ones shape the universe. And memory is not just about the past, it also shapes the future. Neuroscientists have found that the same brain structures used to recall memories are also used to imagine what has not yet happened. When you picture tomorrow's breakfast, you use the same circuits that recall yesterday's. Memory and imagination are two sides of the same coin. This means that the edges of memory also set the edges of our ability to think about the future. If you cannot remember the past, you cannot imagine what comes next. Time, in this sense, depends on memory to exist at all in experience. There are also moments when memory fails more dramatically. People with amnesia, whether from injury or disease, may lose entire sections of their personal history. For them, time collapses inward, reduced to what remains. A person might forget decades, waking to a present unmoored from continuity. The edge of memory has moved closer, cutting off large swaths of the past. In such cases, the subjective flow of time is altered, narrowed to a smaller span. The past beyond that edge is gone, unreachable, just as distant galaxies are hidden beyond the cosmic horizon. Diseases like Alzheimer's bring this into even sharper focus. As memory deteriorates, the continuity of time itself unravels. A person may live more in fragments than in sequences, the thread of time breaking into disconnected pieces. The psychological arrow weakens, and the borders of memory shift inward. For caregivers and loved ones, it is heartbreaking to watch. For science, It is a reminder that time is not just an external dimension, but also an internal experience, one that can erode and end within a single mind. Forgetting also has a functional role. If we remembered everything, our lives would be unbearable. Imagine recalling every detail of every moment, every word spoken, every face seen, every breath taken. The flood of information would overwhelm us. Forgetting allows us to filter, to highlight what matters and discard what doesn't. It creates a manageable narrative. The edges of memory are not failures but features. They shape a timeline that is livable. Just as the universe hides regions beyond horizons, our minds hide events beyond forgetting. Both kinds of edges create order out of overwhelming complexity. Psychologists sometimes describe memory as reconstructive rather than archival. We don't simply pull out recordings of the past. We rebuild them each time we remember, piecing together fragments, filling in gaps, reshaping details. That means memory itself is fluid, and the edges of forgetting are always shifting. What we remember today may not be the same as what we recall tomorrow. Time in the mind is not fixed. It warps and bends like space-time itself. This connects to our sense of identity. Who we are is largely defined by what we remember. Childhood experiences, life milestones, relationships, all of these form the narrative of self. When memory fails that narrative phrase, people with amnesia may lose not only their past but also their sense of identity. Without memory, the continuity of self collapses. In that sense, memory is not just about time. It is time lived from within. Its edges are the edges of our own existence. And there are other psychological borders as well. Trauma can create sharp edges, moments so painful that the mind walls them off, refusing to recall. These blank spots become gaps in personal history, places where time is blocked. Sometimes those memories resurface later, but sometimes they remain inaccessible, like sealed chambers in the archive of the mind. Again, the parallel with cosmic horizons is striking. Just as some regions of the universe are forever hidden from view, some regions of memory are hidden from ourselves. Dreams offer another perspective. In dreams, time often behaves strangely. Hours may pass in seconds, or seconds may stretch into hours. Events can shift out of sequence, blending past and future in ways that feel natural within the dream, but nonsensical upon waking. Dreams remind us that our perception of time is constructed, not given. It can warp, bend, and even break apart depending on the state of the brain. In this way, dreams are small laboratories of time psychology, showing us that the flow we take for granted is not as stable as it seems. Forgetting also shapes how we perceive the present. Without memory, the present moment would have no thickness. It would be an instant with no context. But because we remember the immediate past and anticipate the immediate future, the present feels stretched, like a window that includes more than a single tick. When forgetting encroaches, that window narrows. The present becomes thinner, more fragile. The borders of time press inward, shrinking the span of experience. All of this shows that time for us is not just measured by clocks or equations. It is measured by memory and forgetting, by the capacity to link moments into narratives. Our psychological edges are just as important as physical ones. They define where our personal timeline begins and ends, what parts are accessible and what parts are lost. They shape how we live, how we tell stories, how we imagine ourselves. And perhaps most striking of all, they remind us that time's edges are not always cosmic or distant. They exist here, in each of us. The universe has horizons billions of light years away. We have horizons inside our minds, defined by what we can recall and what we cannot. Both kinds of horizons show us that time is not infinite from our perspective. It has edges, and those edges are where meaning arises. As we carry this thought, we can see how the personal and the cosmic mirror one another. Just as physics finds edges where theories break down, our own lives find edges where memory and identity break down. Both reveal time as fragile, contingent, and bounded, and both invite us to wonder, if time has such borders in our minds, might it have others in culture, in mathematics, or in the very structure of the universe itself? When we think about time, we often assume that the way we measure and imagine it is universal. Clocks tick in seconds, calendars divide days into months and years, and history stretches like a line from past to future. But that's not the only way people have thought about time, nor is it the way all people still think about it. Cultures across history and around the world have mapped time in different ways, creating patterns and meanings that reveal as much about human imagination as about the cosmos itself. To explore the edges of time fully, we need to understand how civilizations have drawn its contours in their own terms. In the West, influenced by Greek philosophy, Judaism, Christianity, and later modern science, time is often pictured as linear. It has a beginning and an end, a straight path that moves in one direction. This linear view of time frames history as a story, with creation, development, climax, and conclusion. It also underpins much of modern physics, where time is a parameter that stretches from the Big Bang into the far future. The line is a powerful metaphor, one that shapes not just science but culture, law, religion, and identity. But not all civilizations see time this way. Many cultures view time as cyclical. The ancient Mayans, for example, built elaborate calendars that mapped repeating cycles of days, months, and larger cosmic ages. For them, time was not an endless line, but a set of interlocking wheels, each cycle repeating after it completed. Hinduism also sees time as cyclical, with vast cosmic ages called yugas repeating endlessly. Creation, preservation, and destruction form a rhythm that repeats through infinite cycles. In these traditions, time does not have a final edge. It loops, like a circle with no beginning or end. Other traditions take yet different approaches. Some indigenous cultures see time as a spiral, blending the linear and cyclical. The spiral allows for repetition but also for progression, a sense that cycles repeat but never exactly the same way. In this view, time is not a static wheel but a dynamic spiral, carrying life forward while returning to familiar patterns. Planting, harvesting, rituals, and seasons are experienced as recurring, but each recurrence brings new lessons and new growth. The way a culture imagines time shapes the way it lives within it. In linear cultures, history is often thought of as progress. The future is new, unprecedented, and better than the past. In cyclical cultures, the future is less about novelty and more about harmony, about returning to balance with rhythms that repeat. In spiral views, the emphasis is on continuity with change, the idea that growth comes through revisiting patterns in new ways. Each of these cultural maps sets different edges for time. One sees an ultimate beginning and end, another sees no end at all, a third sees renewal as both edge and continuation. Calendars themselves embody these views. The Gregorian calendar, used widely today, reflects a linear system, counting years upward from a fixed point. Other calendars, like the Mayan long count or the Hindu calendar, track repeating cycles. Lunar calendars mark the months by the phases of the moon, repeating endlessly. Each calendar encodes a map of time, telling its users where they stand in the flow and where its edges lie. For us, the edges of the year are December and January. For others, the edges are solstices, harvests or festivals, times when cycles complete and begin again. These cultural views also shape memory. In linear traditions, memory often takes the form of history, a chronological record of events moving forward. In cyclical traditions, memory may take the form of ritual, repeating actions that keep the past alive in the present. Each performance of a ritual is both a repetition and a renewal. The past is not gone. It returns again and again at the appointed time. In this way, the psychological edges of memory are softened by cultural cycles. Forgetting is less absolute when the past is reenacted continually. It is striking how deeply these cultural maps of time affect identity. In modern linear societies, people often see themselves as moving along a personal timeline: childhood, education, work, retirement, old age. Life is a line with a beginning and an end. In cultures with cyclical views, life may be seen as part of a larger pattern of rebirth and renewal. Death is not the edge of time, but a transition into another cycle. In spiral views, personal growth may be pictured as revisiting themes of life at deeper levels, like a melody repeating with variations. Each view creates different edges, different meanings for beginnings and endings. Even language reflects these differences. In English, we say the past is behind us and the future is ahead. Time is mapped onto space as a line. In Aymara, an indigenous language of South America, the mapping is reversed. The past is in front because it is visible and known. The future is behind because it is unseen and unknown. This spatial metaphor shifts the edge of time. Instead of facing the future, you back into it, unable to see what is coming. The cultural map of time is written directly into the way people speak. Mythologies offer further examples. In Norse mythology, time ends in Ragnarok, a great destruction followed by renewal. The edge is real, but it's also a doorway to repetition. In Christian theology, time ends with judgment, a final culmination beyond which lies eternity. In Buddhism, time has no ultimate edge, because rebirth continues until enlightenment breaks the cycle. Each vision sets a boundary and then interprets it differently, as finality, renewal, or transcendence. These maps of time are not just intellectual curiosities. They shape how people live and die, how they value the present, how they treat the past. In cultures that see time as cyclical, there may be less anxiety about the future, because what has been will return. In cultures that see time as linear, there may be more urgency, because the line is finite and each moment is unique. In cultures that see time as spiral, there may be a balance between the two, with recognition of patterns but also openness to growth. Science itself has not been immune to these cultural influences. Early Western cosmology, shaped by linear views, looked for beginnings and ends, creation, apocalypse, origin, fate. Eastern traditions, shaped by cycles, anticipated ideas of oscillating universes with cycles of expansion and contraction. Even in physics, the cultural maps of time have left their mark, guiding what kinds of theories seem natural or compelling. When we step back and compare, what we see is not a single truth, but many. Time has been imagined as line, circle, spiral, flow, even as a vast web. Each map emphasizes different edges. The line emphasizes birth and death. The circle emphasizes repetition. The spiral emphasizes growth through return. Each map helps people navigate their lives, giving structure to the mystery of time. And just as the universe has multiple horizons, so too do cultures. There is no single way to mark the edges of time. There are many shaped by language, ritual, history, and imagination. Together they form a rich mosaic of human attempts to understand the ungraspable. As we sit with this, it becomes clear that cultural maps of time are not just descriptions, they are tools. They help people face uncertainty, mortality, and change. They set boundaries for meaning, not just for events, and they remind us that the edges of time are not only out there in the cosmos, they're also drawn in here, in the ways civilizations shape their own stories. Beyond physics and culture lies the personal. What about the edges of time in each individual life? Not just memory, not just forgetting, but the personal boundaries that define when our own timeline begins and ends. When we pull away from vast cosmological horizons and ancient cultural maps, we inevitably arrive at something more intimate. The edges of time are not only out there in the universe, or written in the language of civilizations, they're also within us. Each life is a stretch of time with its own beginning and its own end. For us as individuals, those edges are birth and death. They frame our entire existence, even though we rarely think of them that way. Consider birth. For each of us, it is the moment our personal timeline begins. Before it, time certainly existed. The universe stretched back billions of years, cultures rose and fell, events unfolded. But for us, none of that was part of our lived experience. Our personal time begins with the first breath, the first awareness, the first flickers of memory. Everything before is inaccessible, much like the regions of the universe beyond the cosmic horizon. Others can tell us stories, show us records, describe what happened before we were born, but for us those stories exist only as second-hand knowledge. They are outside the horizon of our personal time. The early years of life highlight this even more. Few people can recall anything from their first years, a period psychologists call childhood amnesia. Our brains at that stage are still developing the structures necessary for long-term memory. The result is that, though we lived through those moments, they are lost to us. Our personal timeline, in terms of memory, starts later than our biological birth. In this way, each person has not just one beginning, but several. The biological beginning, the remembered beginning, and the narrated beginning, passed down through family and culture. Each is an edge of time in a different sense. On the other end lies death. Like birth, it is both universal and absolute. Whatever lies beyond it, if anything, is hidden from us. From the inside, it is the end of personal experience, the point where memory, awareness, and the flow of moments all stop. From the outside, it is a transition marked by those who remain, but for the person themselves, it is the boundary of time. Just as we cannot imagine before our birth, we cannot truly imagine after our death. Both are edges where personal time dissolves into nothingness. Between these edges, life unfolds like a stretch of film, limited in length, unique in content. Some films are long, others short. Some are filled with drama, others with quiet repetition. But all are bounded by beginning and end. For us, those edges define what time means. We measure not in billions of years or cosmic horizons, but in decades, seasons, milestones. Personal time is scaled to the human clock, and its edges are as meaningful to us as the Big Bang or heat death are to the universe. The awareness of these edges shapes how we live. Knowing that life is finite gives urgency to our actions. It motivates us to seek meaning, to create, to connect, to love. At the same time, it can create fear, the dread of an approaching edge we cannot avoid. Cultures respond to this in different ways, some with rituals of remembrance, others with beliefs in afterlives or rebirths. But the underlying fact remains. For each of us, time has personal edges, and they are inescapable. Think of how we mark those edges socially. Birthdays celebrate the passage of years since the beginning. Funerals mark the final boundary. In between, we know anniversaries, milestones, and transitions. These rituals anchor us in time, reminding us of the edges that define us. Even the smallest gestures, lighting candles on a cake or placing flowers on a grave, are ways of acknowledging the finite nature of personal time. The human body itself keeps time. Biological rhythms, circadian cycles, the steady beating of the heart, all of these are clocks within us. They measure the passage of hours and years, ticking until they stop. Our very cells age, accumulating changes that mark the passage of time at a microscopic level. Telomeres shorten, DNA accumulates damage, proteins misfold. These processes are reminders that time is not just external. It is written into our biology. We carry the arrow of time in our bodies, as surely as the universe carries it in entropy. Personal time also has its own psychological flow. As children, time feels vast, some as endless, a year an eternity. As adults, time accelerates, years slipping by quickly, decades folding together. This shifting perception is another kind of edge. The same span of time feels different at different stages of life. The edge of childhood, the edge of middle age, the edge of old age. All are thresholds where the character of time changes, even though the clock ticks the same. There are also moments when time feels suspended. Waiting and anxiety moments stretch unbearably. Joyful experiences, by contrast, seem to vanish in an instant. These variations remind us that time is not only measured by clocks, it is measured by the mind, by the intensity of experience, by memory. The edges of perception can warp personal time as surely as gravity warps space-time. What about the final edge itself? Philosophers and poets have long tried to imagine death as an edge of time. Some see it as a cliff, abrupt and absolute. Others see it as a doorway, a transition into something beyond. Still others see it as a return to nothingness, the same nothingness that framed our existence before birth. Whatever interpretation one chooses, the personal edge of death is as absolute as the cosmological edge of the Big Bang. It defines the boundary of personal time, the frame within which all else occurs, and yet paradoxically, we cannot experience our own edges, we cannot remember our birth, nor can we live our death. Both are outside experience by definition. This makes them strange edges, ones that shape everything we know while remaining forever inaccessible. They are like horizons in the mind, defining our existence without being part of it. For many, the awareness of these edges leads to a search for meaning. If life is bounded, how should it be lived? Some answer with religion, imagining continuity beyond the edge. Others answer with philosophy, embracing the finiteness itself as what gives life value. Still others answer with art, creating works that outlast personal time. Each response is an attempt to make peace with the edges of the human clock. And there is another dimension to consider. Just as the universe has collective time measured in billions of years, humans have collective time measured in generations. Even after an individual's edges are reached, collective time continues. Children, communities, cultures, species, all carry time forward beyond the personal horizon. In this sense, the edges of individual time are not the edges of all time. They are part of a larger flow that stretches beyond us. This does not make the personal edges any less real, but it places them in context, just as the observable universe places our cosmic horizon in context. We are finite within infinity, bounded within unboundedness. Our clocks begin and end, but they tick within larger clocks, cultural, planetary, cosmic, that continue beyond. This layering of time, from personal to collective to cosmic, gives us perspective on our place in the universe, and it reminds us that the edges of personal time, though absolute for us, are not the end of the story. They are part of a greater pattern, one in which beginnings and endings are continually unfolding at different scales. In this way, the personal edges of birth and death connect back to the cosmic edges of the Big Bang and heat death. Both define spans of time within larger contexts. Both remind us that time, at every level, has horizons, from personal edges to collective ones, from the human clock to the universe's clock. The question grows larger once more. What happens when we imagine not just one timeline, but many? Not just one universe, but possibly countless others, each with its own edges of time. When scientists speak about the universe, they often turn to mathematics as the language of choice. Equations do not tire, they do not forget, and they do not waver in emotion. They offer precision where words falter. But equations themselves sometimes hint at limits, places where their smoothness gives way to infinities, singularities, or undefined values. In those moments, even mathematics seems to confront boundaries. If time itself has edges, then perhaps equations too can be said to have them. One of the clearest examples is the singularity. In general relativity, when we calculate the behavior of space-time near the center of a black hole, the equations give infinite curvature. At the Big Bang, when we trace the universe backward, the equations again give infinite density. In both cases, the mathematics points to a breakdown. Numbers diverge, values become infinite, and the neat framework collapses. These infinities are not just large numbers, they are signs that our description has reached an edge. The equations are no longer capable of describing reality. Singularities raise profound questions. Are they real features of the universe, or are they simply artifacts of incomplete theories? Many physicists suspect the latter. Just as Newton's laws fail at high speeds and are replaced by relativity, relativity may fail at singularities and need replacement by quantum gravity. In this sense, the infinities in equations are warning signs, markers of boundaries where new mathematics is needed. They are edges in knowledge, revealed not by telescopes but by symbols on a page. The idea that equations can end is unsettling, because we often think of mathematics as limitless. Numbers stretch to infinity, patterns repeat endlessly, equations can be extended as far as we like. But when those equations are applied to the physical world, they sometimes tell us they cannot go further. They produce contradictions, undefined results, or infinities. That is how we know we've reached a boundary. Not necessarily a boundary of the universe itself, but a boundary of description. This happens not only in relativity. Quantum mechanics too reveals mathematical edges. The Schrödinger equation describes the evolution of a quantum system smoothly over time. But when measurement occurs, the equation is replaced by the collapse of the wave function. This collapse is not described by the equation itself. It is an extra rule, added on top, that marks the boundary between quantum probabilities and observed reality. Why this happens, and how, remains one of the great puzzles of physics. The mathematics works beautifully until that edge, and then something different takes over. Another place where equations face limits is chaos theory. Certain systems, though governed by simple mathematical rules, are so sensitive to initial conditions that their future becomes unpredictable. Weather is a classic example. The equations of fluid dynamics can describe it. But beyond a certain horizon, predictions break down. Small differences amplify until the outcome is uncertain. Here, the edge is not an infinity, but a horizon of predictability. The mathematics does not fail outright, but our ability to apply it does. The edge is practical rather than absolute, but it feels just as real. Mathematics also gives us paradoxes, boundaries where logic seems to fold back on itself. Consider Zeno's paradoxes, where motion is broken into infinite steps, suggesting that movement should be impossible, or Gödel's incompleteness theorems, which show that in any consistent mathematical system rich enough to describe arithmetic, there are truths that cannot be proven within the system itself. These results remind us that even mathematics has boundaries, places where certainty cannot extend. They are edges not of physics, but of logic itself. So when we ask whether equations can end, the answer is yes, in multiple senses. They can end in singularities, where infinities appear. They can end in collapses, where smooth evolution breaks into sudden change. They can end in horizons, where prediction gives way to unpredictability. They can end in incompleteness, where truth outruns proof. Each of these endings is different, but all show that mathematics is not infinite in its power to describe. It has edges, and those edges shape our understanding of time and reality. But there is another side to this. Sometimes equations suggest that boundaries are illusions. Take the example of the number line. It stretches infinitely in both directions, yet at any given moment, we occupy only a finite segment of it. The line has no edge, but our position on it does. Similarly, in calculus, infinities can sometimes be tamed. Diverging series can be regularized, infinities cancelled out, singularity smoothed. In these cases, mathematics seems to reach past its own edges, showing that what looked like a boundary was really a transition into a deeper framework. This suggests that mathematical edges are often signals of new understanding waiting to be found. The singularity at the Big Bang may be an invitation to discover quantum gravity. The collapse of the wave function may be a hint that our picture of observation is incomplete. Chaos may be a reminder that predictability has horizons, not absolutes. Gödel's theorems may be a pointer to the richness of truth beyond formal proof. Each edge in mathematics is both a stop sign and a doorway. it halts progress in one direction while opening questions in another. And here, once again, the personal and the cosmic meet. Just as memory fades at the edges of our lives, equations falter at the edges of our knowledge. Both are boundaries that shape how far we can see and how much we can know. Both remind us that edges are not always failures. They are the places where meaning is concentrated, where discovery becomes possible. Mathematics, after all, is itself a kind of time. Equations unfold step by step, carrying us from one point to the next. Proofs proceed in sequences. Calculations build on prior results. In this sense, mathematics has its own arrow of time, moving from premises to conclusions. When that arrow meets an edge, an infinity, an incompleteness, a paradox, it is as though time itself has encountered a boundary. The analogy is not perfect, but it helps us feel the kinship between the edges of equations and the edges of time, and so we can see that even in the abstract realm of symbols, the question of edges arises. Can equations end? Yes. And when they do, they remind us that our tools are finite, our maps incomplete. But they also remind us that every edge is a place of potential, a horizon from which new landscapes may one day be revealed. Once we admit that time might have edges, the imagination quickly begins to wonder what could lie beyond them. Physics, when it meets its own limits, often produces speculation that sounds more like philosophy than strict science. Yet speculation has always been part of the scientific process. Before evidence is gathered, ideas must first be dreamed. In cosmology, some of the most ambitious ideas deal directly with time, whether it loops, whether it cycles, whether our universe is only one among many, each with its own edges and its own flow of time. One of the oldest speculative visions is the cyclical universe. Long before modern cosmology, many traditions imagine the cosmos as endlessly repeating. In Hinduism, the ages of the world cycle through creation, preservation and destruction, only to begin again. In ancient Greece, philosophers like the Stoics imagined the universe burning in a great conflagration, then being reborn in identical form. In these views, time does not end but turns back on itself. The edges are not final walls but turning points, moments of transition into new cycles. Modern physics has explored similar ideas. Some versions of cosmology propose that the universe expands from a Big Bang, slows, collapses in a big crunch, and then rebounds into another expansion. The cycle could repeat forever, each universe following the last in an eternal rhythm. In such models, the arrow of time may even reverse during collapse, only to reset at each new beginning. If this were true, then what we call the beginning of time might only be the latest cycle, one among countless others stretching into the past and future. Another speculative idea is the time loop. Instead of endless cycles, imagine a single universe in which time itself is circular. Travel far enough into the future and you return to the same moment again. Everything repeats exactly, endlessly. This idea, sometimes called eternal recurrence, was considered by philosophers like Nietzsche, who asked what it would mean to live a life that would repeat forever, in every detail. In physics, certain cosmological solutions to Einstein's equations allow for closed time-like curves, paths in space-time that loop back on themselves. Whether such paths can exist in reality is debated, but the mathematics allows them in principle. If time is a loop, then the edge is also the beginning, and the future is identical to the past. These ideas stretch our sense of meaning. If everything repeats, then are our choices real, or are they fated to recur endlessly? If the universe cycles, then is progress possible, or do we simply return to the same states again and again? These questions show that speculation about time is not only scientific, but also existential. It forces us to confront what kind of story we are living in, a line, a circle, or something stranger. And then there is the multiverse. The idea that our universe may not be the only one has gained attention in recent decades. One version comes from cosmic inflation, the theory that the universe expanded rapidly in its earliest moments. Some models of inflation suggest that this expansion never completely ends. Instead, it continues in different regions, creating bubbles of space-time that become separate universes. Each bubble may have its own laws of physics, its own constants, its own kind of time. Our universe would be just one bubble in an infinite froth, with countless others beyond our horizon. Another version comes from quantum mechanics. The many worlds interpretation suggests that every quantum event branches into multiple outcomes, each realized in its own universe. In this view, time itself branches, splitting into different paths with every decision, every particle interaction. The multiverse becomes a vast tree of possibilities, with time edges multiplied endlessly across the branches. For us, this is unsettling to imagine, because it suggests that every choice we make exists alongside countless others, all equally real. The edge of time becomes less about endings and more about divergence. There are even proposals that multiverses may have different kinds of time altogether. Some universes may have more dimensions of time, not just one arrow but several. Others may have time running in a reverse relative to ours. If such universes exist, then the edges of time as we know it may only be local. Beyond them, other forms of time may unfold, incomprehensible to us. These speculations may sound fantastical, but they are motivated by attempts to explain deep puzzles in physics, from the fine-tuning of constants to the behavior of entropy. What all these ideas share is a refusal to accept that the edges we see are the only ones that exist. Cycles, loops, and multiverses all suggest that beyond our boundaries there may be more time, more universes, more possibilities. These ideas are not proven, and they may never be testable, but they serve a role. They remind us that the edges we encounter in equations and observations may not be absolute. They may be the limits of our view, not the limits of reality. Speculative science often walks a fine line. Too far, and it becomes unfalsifiable, drifting into pure imagination. Too cautious, and it misses the chance to anticipate new discoveries. The best speculations balance daring with discipline, using imagination to push against the edges of knowledge while remaining tethered to what is known. In cosmology, this balance is particularly delicate because the universe itself offers so few chances to experiment directly. Much of what we propose about cycles, loops, or multiverses is extrapolation. Yet even extrapolation has value because it shapes the questions we ask and the directions we search. These ideas also echo our personal sense of time. The thought of cycles resonates with the rhythms of nature, the seasons, the turning of generations. The thought of loops resonates with memory, with the way we relive moments in our minds. The thought of multiverses resonates with imagination, with the possibilities we consider but do not live. In this way, speculative science connects the cosmic to the intimate, showing that the patterns we dream at large scales are not so different from the ones we live at small scales. And perhaps this is the deeper reason why speculation matters. It allows us to inhabit possibilities beyond our current edges, to imagine what lies past the boundaries of time as we know it. Whether those possibilities turn out to be true or not, they expand our sense of what reality could be. They remind us that time, which feels so familiar, may contain forms and edges far stranger than we can yet conceive. If cycles, loops, and multiverses are possibilities for the cosmos, then what about the time we're living right now? What does it mean to stand in the present, at the edge between past and future, with all of these possibilities stretching around us? When we think about time's edges, we often picture them as distant boundaries, either at the beginning of the universe or at its far-off end. We imagine the Big Bang as one wall and heat death as another, with billions of years stretched between them. But there is another edge of time that is always with us, immediate and unavoidable. That edge is the present moment. The now is the point at which the past ends and the future begins. It is the moving boundary we live upon constantly, the thin edge of the knife where time is experienced. This edge is strange because it is both obvious and elusive. We all know what the present feels like. It is the moment we are conscious, the moment unfolding right now. But try to define it, and it slips away. If you say the present is this second, by the time you finish the thought, the second has passed. If you say it is the duration of a thought, then thoughts overlap and stretch, making the present ambiguous. If you try to measure it physically, perhaps as a slice of space-time, relativity complicates the picture. Different observers, moving at different speeds or experiencing different gravities, disagree about which events are simultaneous. There is no single, universal now. There are only local nows, each relative to perspective. And yet, subjectively, the present feels absolute. We cannot step outside it. We cannot visit the past except through memory, nor the future except through anticipation. The present is the edge we are always standing on, even if we cannot pin it down. In this way, the now is a kind of temporal horizon. It divides what is accessible from what is inaccessible, what is already fixed from what is still open. Like a horizon, it moves with us. Like a horizon, it defines the limit of what we can see. The psychology of the present reveals how flexible this edge can be. In ordinary consciousness, the present moment feels like a short span, perhaps a few seconds long. It includes just enough of the immediate past to form continuity, and just enough anticipation to form expectation. Neuroscientists sometimes call this the specious present, the window of time we perceive as now. It is not an instant, but a span. Wide enough for a melody to make sense, for a sentence to be understood, for motion to appear continuous. Without this span, the world would break into fragments. This span varies depending on context. When we are absorbed in something we enjoy, the present feels expansive, flowing easily. When we are anxious or waiting, the present contracts into sharp, uncomfortable instants. Time seems to crawl. Drugs, meditation, and altered states of consciousness can also expand or shrink the present, stretching it into eternity or compressing it into flickers. These changes show that the edge of now is not fixed. It is elastic, shaped by the brain's rhythms, attention, and state. Memory and anticipation are what give the present its thickness. Without memory, the present would collapse into an instant with no continuity. Without anticipation, it would have no direction, only a frozen snapshot. Together, memory and anticipation extend the edge, making it feel like a flowing river rather than a point. This means that the present is not just the boundary between past and future. It is an active construction, built moment by moment in the brain. Relativity deepens the mystery. According to Einstein, simultaneity is relative. What one observer considers the present may not match what another considers the present. For someone on Earth and someone on a spaceship moving near light speed, their nows are different slices of space-time. There is no single cosmic now, no universal present stretching across the universe. Each observer carries their own edge of time, defined by their frame of reference. The present in physics is plural rather than singular. This idea unsettles our intuition. We like to imagine that there is one grand present moment shared by all, a kind of universal stage on which the play unfolds. But relativity denies this. It says that the stage is local, shifting with each perspective. That does not change how we experience the now, but it shows that the present is not as absolute as it feels. It is another reminder that time is more flexible than we imagine. Philosophers have long debated the status of the present. Some argue for presentism, the idea that only the present truly exists. The past is gone, the future unreal, and only the now is real. Others argue for eternalism, the idea that past, present, and future all exist equally, like different points on a line. In this view, the present is not special. It is simply where we happen to stand in the block of space-time. Still others propose the growing block theory, in which the past and present exist but the future does not yet. Each of these philosophies tries to capture the elusive edge of now, and each offers a different picture of time's reality. Whichever view one takes, the fact remains that our lives are lived on this edge. The past is fixed. The future is open. The present is where choices are made, where experience unfolds, where reality feels most immediate. In this sense, the now is the most intimate edge of time. It is always with us, always moving, always vanishing as soon as it appears. Think of how this affects our sense of meaning. If the present is the only real moment, then the value of life lies in inhabiting it fully. If the past and future are equally real, then the present is just one slice of a greater whole, and our place within it is less unique. If the future is not yet real, then the present carries the weight of creation, the moment in which reality comes into being. Each view shifts the significance of the now, shaping how we think about its edge. The present is also where time's edges become personal. Birth and death mark the outer edges of our timeline, but the now is the inner edge we always stand on. It is the point where our personal time touches the universe's time. Every heartbeat, every breath, every thought unfolds on that edge. Without it, we could not live, because life is nothing more than a sequence of nows. And yet, the now is elusive. Try to hold on to it, and it slips away. By the time you notice it, it is already gone, replaced by another. This paradox makes the present feel both real and unreal. It is the only moment we live, and yet it cannot be captured. It is like standing on a shoreline where the waves continually erase the sand beneath your feet. The present is always here, always vanishing. This mystery invites us to see the now as more than a psychological trick or a point in physics. It is an edge that carries both intimacy and infinity. Intimacy, because it is where we live our lives. Infinity, because it is always renewed, always stretching forward, never exhausted. The now is an edge that never ends, a boundary that continually moves. It is perhaps the most paradoxical of time's edges, because it is both the narrowest and the widest. If the present is the edge we live upon, what happens when we step back and see it as part of the greater mystery of time? How does the drifting now connect the cosmic horizons, the quantum puzzles, the cultural maps, and the personal clocks? We have followed time across vast distances, from the first instant of the Big Bang to the far possibilities of heat death, crunches, rips, and rebirths. We have looked closely at the way time bends near black holes, how it dissolves at quantum scales, how it emerges and vanishes in the structures of the mind. We have seen it mapped in cycles, spirals, and lines by cultures across the world, and we have felt its edges in our own lives, in memory and forgetting, in birth and death, in the mystery of the present moment. At every turn, time has revealed itself as both familiar and strange, intimate and infinite. And now, as we drift into the final stretch of reflection, we find ourselves hovering at another edge, the edge between wakefulness and sleep, between thought and dream. There is something fitting about ending here. Time itself, as we have seen, has many boundaries, but the border between waking and dreaming is one we cross every night, one we know intimately. In waking life, time feels steady, directional, ordered. In dreams, it often behaves differently. Minutes can stretch into hours, or hours compress into moments. Events can jump out of sequence, blending past, present, and future in ways that seem natural in the dream but uncanny upon waking. Dreams show us that time is not as fixed as we think. It can loosen, warp, even dissolve, depending on the state of consciousness. In this way, dreaming is like a personal laboratory of time. Every night, the brain experiments with temporal edges, rearranging memory, collapsing events, distorting duration. It's as though the mind rehearses the strange behaviours of time we encounter in physics and philosophy, but in its own language of symbols and images. In dreams, the arrow of time can bend, the edges of memory can blur, the present moment can stretch beyond recognition, and when we awaken, we often feel a lingering strangeness, as though we have visited another kind of time entirely. This nightly crossing mirrors the larger themes we've explored. Just as cosmology shows us horizons we cannot cross, dreams show us boundaries we cannot fully hold on to. Just as mathematics reveals infinities where equations break down, dreams reveal gaps where memory fails to capture what just unfolded. Just as personal time is bounded by birth and death, dream time is bounded by waking and sleeping. In both cases, the edges are absolute from the inside. While you dream, you cannot imagine being awake. While you are awake, you cannot fully return to the dream. The border is clear, even if the details are fuzzy. And perhaps this is why dreams feel so mysterious. They remind us that time is not unitary. There is not just one way to experience it. The cosmos has its edges, and so do our minds. Between them lies the fragile structure we call reality, stitched together moment by moment. When we dream, that stitching loosens. Time frays at the edges, and in that loosening we glimpse possibilities that ordinary waking life keeps hidden. As we drift towards sleep, it is worth remembering that time is not just something to be measured and analysed. It is also something to be felt, lived, and experienced. We live within its flow, but we also carry it within us. Every memory, every anticipation, every heartbeat is part of time's fabric. And every night, as we close our eyes, we step across one of its gentlest edges. We surrender the arrow, we loosen our grip on the present, and we allow ourselves to drift into a borderland where time takes on other forms. The edges of time are vast and varied. Some are cosmic, stretching across billions of years. Some are personal, marking the boundaries of a single life. Some are cultural, shaped by language, ritual, and tradition. Some are mathematical, revealed in equations that falter at infinities. And some are psychological, found in memory, forgetting, and dreams. Each edge tells us something about what time is and about what it isn't. Together they remind us that time is not absolute, not guaranteed, not endless. It is a phenomenon with borders, horizons, and mysteries. And yet, far from diminishing its meaning, these edges enrich it. Time is precious precisely because it has limits. The present matters because it is fleeting. Memories matter because they are fragile. The universe matters because it has a beginning and perhaps an end. Without edges, time would be endless and shapeless, a blur with no contours. With edges, it becomes a story, one we can live, remember, and wonder about. So as we drift here, at the border of dreams, it is worth pausing to appreciate the strangeness and the beauty of this fact. Time is the most familiar thing in our lives and yet the least understood. We live within it constantly, and yet we cannot step outside it. We measure it, map it, describe it with equations, and still it slips away. It is both our most constant companion and our greatest mystery. In a way, this mystery is comforting. If time can have edges, if it can begin and end, if it can bend, dissolve, or transform, then it is not something rigid or unchangeable. It is something alive, dynamic, perhaps even creative. It allows for stories, for change, for growth, and in that it allows for us. Without time, there would be no lives, no memories, no dreams. Whatever edges it may have, we are fortunate to live within them. As the mind softens into rest, the edges of thought blur, just as the edges of time do. The present moment stretches, memory loosens, and anticipation fades. This is not an end, but a transition. It is the nightly reminder that time itself is not always what it seems. Beyond the border of wakefulness lies another kind of time, one we enter without fear, one we leave without effort, one that reminds us of the mystery at the heart of existence, So here, at the drifting edge of the now, at the border of dreams, we can let go of the need to measure or understand. We can allow the flow of time to carry us without resistance, without control. We can rest in the awareness that time has many edges, and that for this moment it is enough to simply be carried by one of them, gently into sleep. Thank you for spending this time together, exploring the edges of time and the quiet mysteries they hold. If you found this journey calming, and if you'd like more gentle explorations like this, you can always like the video, subscribe, or share it with someone who might also find comfort in it. For now, let the thoughts of time drift into the background. Allow yourself to settle, to rest, to simply be carried by the stillness of this moment. Wherever you are, whatever hour it is, I wish you peace, calm, and deep, refreshing sleep. Good night.